Okay, let's get started for the day. So our first speaker is. Our first speaker is Peter Kairos, who is a staff research scientist at Google, where he focuses on researching and building private, secure, and trustworthy AI technologies. Before joining Google, he was postdoc at Stanford. He received the 2015 ACM Sigmatrix Best Paper Award, Qualcomm Research Center Padwani Scholarship, the 2016 Harold Olson Award for Excellence in Undergraduate Teaching from UIUC, and the 2021 ACM Communication, the ACM Communication Security Best Paper Award. I'm really interested in, your talk, Peter. Take it away.
Thank you. Yeah, thanks a lot for inviting me, and I'm really excited to be here. So, as the title suggests, I'm going to try to reflect on some of the progress that we made over the years in this area, and I'll try to project a little bit towards the end about what I think may be interesting moving forward. But before we move into reflections and projections, let's start with what's top of mind for a lot of people. So traditionally, the way we have done machine learning is for a specific task in the specific domain, we would train a model on that data. And so we would have across different modalities and different data domains, specialized models with training on data from that domain. And then recently, what happened was a bit of a paradigm shift where people advocated for what's now called as foundation models, where you would train across many modalities and many different domains. And these models are obviously proving to be extremely powerful for a lot of things, and we like them a lot because they have so many properties like zero-shot learning and few-shot learning, and they can generalize across many tasks, many domains, languages, and modalities, and then we can adapt them on certain downstream tasks. And so it's a very fast-moving area. I have a few examples of some of these foundation models, starting with BERT, all the way down to Gemini, which was announced last week. Lots of progress from many different companies, including even startups and smaller companies. And so we've shown that these things are powerful, and they're useful for a variety of things. We're not there yet, but we have made a lot of progress. And this is all great. So the reason why I bring it up is because a lot of people are asking, if we are there, should we use anything that's not public data? These models are trained on web data, open data, and it begs the question, if they're really good and becoming really powerful for a lot of things, does that mean we would never need to use non-public data? And so I'm arguing that we actually do need public data, non-public data. And the reason being, if you look at this diagram, the blue distribution represents the data that these LLMs are seeing. You have your Wikipedia, Reddit, you have a lot of books, blog posts, chats, research papers, so on and so forth. So they're seeing a lot of rich data, and that's why they're being very useful at a variety of tasks across multiple languages and even modalities, and that's great. But these models are not really trained on things that are necessary for things like medical applications, or even applications that we have on our phone, like emails and calendars and chats with our friends. So they're not seeing things like medical patient data. They're not seeing user location data. They're not seeing user chats and emails. And there's obviously a reason for that, which is because these types of data are actually very sensitive. So if you look at all these LLMs, they've made a lot of progress, but if you have noticed since GPT-4, improving upon the accuracy of these models has been quite challenging. And some people argue that even if we throw more compute, more parameters, and even more tokens for training, we're not going to improve the performance of these models by a whole lot. We really need to tap on other sources of data in order for us to make progress in the field. And this is not surprising. At Google, actually, we realized that even before LLMs were very cool. And you can see here for a variety of tasks, going from the Gboard next word prediction to the hot word misrecognition, all the way to smart text selection. Whenever we trained on in-domain data, non-web, non-public data, we were able to improve performance anywhere between 10% to 24%. And these are all trained with federated technologies on device. So we're doing it with some privacy preservation. So you can see that this actually, in the industry, is actually well known. It's not just my own opinion or a thought experiment. So rather than saying these LLMs do not benefit from training with in-domain data, I think we should be able to say that high-quality in-domain data is going to be required for improving the efficiency and accuracy of these models in production for tasks. And that's really a key takeaway message. But if we've made the case for it, and if we all believe that this is true, then this begs the question of how are we going to obtain this data, and how are we going to do it in a way that's actually privacy preserving? And so back in 2015 at Google, researchers were confronted by a few choices. Either they would not use any private data to improve these models in production, just use whatever you can get from web data, or you can ignore all the risks, especially the privacy risks, and log the data and use it centrally anyway to train, or you had to invent a new technique, a new solution. And what they picked is to actually invent a new solution, and that's when they popularized this paradigm, which is called federated learning and analytics. And so in this paradigm, instead of shipping the data and putting it on the server and training centrally on it, the way you would have traditionally done, you actually push the computation to the edge, you would train on device, and you would only send model updates. And this is something that I think a lot of people in this room have mastered and advanced over the years. But when we want to reason about privacy of this system, we have to actually ask ourselves the privacy of who? There are many actors, all the way from the devices that have the data, to the server itself, to the analyst that's actually submitting that job to train a model or to compute a statistic, all the way to deployment, when we deploy the model to devices for inference. And so we really need to look at the holistic picture. And I think yesterday we were discussing privacy, and probably Michael said that he likes DP because it has this one parameter, it's nice, it's continuous, smooth, but I'm actually going to push back a little bit against it. I'm going to say that boiling down privacy to one number is actually not very healthy, because privacy is a lot more than just one thing. It's not a binary quantity, there or not there. It's not a scalar, it's multifaceted and multidimensional. So let me try to explain what I mean by that. I think we need to separate some concerns for the user, for the platform, and for the verifiers. And these concerns may not be always exactly the same and may not always be even aligned together. So we need, for instance, things like more transparency and auditability and control. We need to let the users decide if they want their data to be actually used for certain computations. They need to understand what are those computations, and they could choose whether they want the data to go into those computations or not. We need to use data minimization, and federated learning is one technique on that front, which is let's not collect anything and everything. Let's try to minimize things as quickly as possible. And then we need data anonymization technologies such as differential privacy in order to ensure that the output of the computation itself does not leak anything sensitive. And finally, we want to be able to verify or falsify some of the privacy claims that we are making. And that is actually very crucial when you train with cryptographic techniques or secure hardware and things like that. So you can see that federated learning by design captures a lot of the data minimization principle. We have minimized data exposure. We're only sending focused minimal updates. We aggregate immediately. We delete all those updates. And then we only share limited things with the analyst that has requested the computation. So the analyst would not see the whole trace of model iterates. Instead, it would only see a few snapshots. And then we do single deployment at the end of the day. So we're reducing the amount of data that we're releasing as we go from left to right in this figure. And we could combine federated learning with a lot of privacy-preserving technologies, such as secure multi-party computation, differential privacy in all its flavor, whether it's local, distributed, or central. We can do privacy attacks on this system, red teaming, so on and so forth, in order to strengthen and formalize the guarantees of the system. And so one of the things that I wanted to touch on in this talk is how we were able to deploy differential privacy in production and the challenges around it. So DP is something that I'm assuming a lot of you are aware of. It tells you that if you were to train a model on a data set compared to a neighboring adjacent data set that only differs by one record, and we'll define that record in a bit, these two models should look a lot alike. Statistically, they should have very similar distributions, because if they have very different distributions, then the absence or presence of that record can be easily detected by an adversary. And so it uses what's known as the max divergence with these two parameters, epsilon and delta, and we want them both to be small. Think of delta as something that's cryptographically small, 10 to the negative 9 or smaller. Think of epsilon as something that should be at least in the single digits, hopefully less than 1. So, but we need to really think about what is the unit of privacy here, because I think this is just as important as the definition of privacy itself. When we say we change a record when we go from D to D prime, what is that record? It could be a single training example, in which we call it example-level differential privacy, or it could be all the training examples that belong to a single user, which we call user-level differential privacy. In fact, in the context of LLMs and language modeling, we can have many different units of privacy. It's not just example level. We can go maybe all the way down to token level, only change one token in a training example. Or you can change the training example, or you can go to user, and so on and so forth. Paragraph, document, organization, etc. And you can see that as we go from top to bottom, we're getting exponentially stronger privacy units, because the protection that we're given using this definition is getting bigger and bigger. Now, in the cross-device federated learning setting, we actually love to use user-level differential privacy because it puts the unit of privacy at the user, and that's meaningful, not just a training example or a token. And the way we apply DP is as follows. There's this algorithm called federated averaging, which is very simple. You compute a number of local SGD steps, and then after that, you send the model update back to the server. So the server aggregates these model updates across a cohort of users, computes some sort of weighted average for them, and then you keep repeating this process many times. So in order to add DP to it, the one thing you would have to change, or actually two things, is you have to bound the user contribution. So whenever you are done computing those local steps, you would clip the contribution that you're giving back to the server. And then you would add Gaussian noise after you aggregate the clipped model updates. So the application of DP itself is very simple, but the devil is in the details. How we compute the privacy and how we analyze it for the system is quite complicated. And particularly, we leverage what's known as privacy amplification via sampling, which says that if you were to select at random a cohort of users, you get a boost in the privacy because the adversary now has to fight the noise that the server adds, that Gaussian noise, and also the uncertainty in the sample of users that were selected for that round. So you can see why it's adding randomness into the system, so it's helping privacy. It gives us better epsilons. And this actually is very critical. If you look at the figure here, this is for training a simple small language model on the Stack Overflow data set. You see that when we use this amplification via sampling, when we are able to select users at random per round, we get much better privacy accuracy trade-offs. So you see we're training the model, test accuracy versus the epsilon, the DP epsilon, and we can get much better accuracy under this uniform sampling. And this has been the bedrock of DP, applying DP to machine learning. But it's actually very difficult in production FL because how would you sample devices uniformly at random? They're not always all available. There's new devices checking into the system and some that are going offline. And there's all these very sophisticated criteria for who can check in versus who cannot, depending on whether the device is charging, idle, so on and so forth. So that really meant that the server cannot really track who's there and sample from that pool. So we had to do something about it. And the way we approached this problem is that we took the literally stochastic gradient descent update equation and we unrolled it. And the first thing you observe when you unroll the SGD update equation is that really what you're doing is you're computing a prefix sum over the updates across rounds. So G1 is the update in round 1, G2 is the update in round 2. So all you care about here is an algorithm that can compute these prefix sums of updates across rounds in a differentially private way. And that is something that, it turns out, in the DP community has been studied. And there's a variety of mechanisms that allow you to do these continual observation DP mechanisms. But we end up with something that's streaming. So we end up with an algorithm that has a state, unlike the one that I showed you 2 slides ago where you add independent Gaussian noise across training rounds. This one actually correlates the Gaussian noise across training rounds. So it's a bit more complicated, and we called it DP-FTRL. There's a reason for that. I'm happy to discuss it after the talk. And so what we were able to do earlier this year is we were able to take all the Gboard language models, it's a family of about 20 models, and train them all again from scratch with differential privacy. So not only are we training them with federated learning, but also with formal provable differential privacy. And in this table, I'm just summarizing a bunch of them. You can see that there's many different languages. You go from German to Spanish and English and so on and so forth. And each language is a population of devices with a certain size, and not all of them will get the same privacy. It depends on how big that population is. That's one key takeaway. If you have a lot of devices from a certain language, which in this example for ENUS, that's English in the continental US, you can achieve a pretty strong DP guarantee. The models we've trained achieve an epsilon of 4.5 with a delta 10 to the negative 10. Whereas if you are in a population that is very small, like the one on the 5th row of this table, you achieve an epsilon that's 13, which is weaker. But the good point here is that we're training all of them with DP. And we were able to actually add secure aggregation into the mix to ensure that the server does not see the individual model updates from these clients. It only sees the aggregate model updates. So that was something that we were able to accomplish quite recently. There's a lot in this area. This is a manuscript that we published 2 years ago. Michael was the editor for this manuscript, and some of the people in the audience are authors on this manuscript. It continues to be relevant today. It has a lot of interesting open questions, and we published a follow-up to it, a field guide to federated optimization with all the interesting constraints on the fairness, robustness, privacy, so on and so forth. But I want to conclude with 2 thoughts here, going back to the opener, which is LLMs and foundation models. And I want to make concretely 2 projections. One is that federated learning is here to stay, in my opinion. First, even for the foundation models themselves, they're being trained on data from very different modalities and groups and data types. And so these federated algorithms, like federated averaging and variance of it, can actually have the potential of improving the performance and the meta-learning capabilities and zero-shot capabilities of these foundation models. But as we said in the first part of the talk, foundation models by themselves are not enough. You need to fine-tune them and then customize and personalize them depending on the data sets as we go from public to non-public data set. And so this is where we probably need to discover ways to shrink the models, to make improvements in terms of memory and compute, push them to the edge. So I believe that federated technologies are here to stay. And the second and last projection I will make is that we may have to change the way we federate. So far, we've been thinking about federated learning as we train exclusively on device, and then we send the model update to the server, which aggregates it possibly with multi-party computation and differential privacy. But maybe we need to do something a little different. We keep the algorithmic structure of federated learning, separating user data as the unit that we want to protect against. But now instead of training on device, because these models can become really big in the tens and hundreds of billions of parameters, maybe we can send them and store them securely in a trusted environment. We can use things like secure enclaves and trusted execution environments. And we, on the server, can have a lot more resources, so we can apply these algorithms in that trusted environment and give some sort of receipt or a certificate that we never computed anything other than what was intended on the data. So this is something we can discuss later today, but I'll stop for now and thank you.
Questions for Peter?
Sorry for sitting so far off. Yeah, it's a nice talk. So I had a couple questions. One was in terms of FTRL is generally popular, optimal for the online setting, while SGD is in the standard setting. Do you know under what cases DPFTRL and DPSGD begin to behave similarly in performance?
Yeah, in fact, there's been a lot of follow-up work on the paper that I showed here, the one which we used in production. And today, there's a version of these algorithms that uses what we call the matrix factorization mechanism. And we can prove, theoretically, that the matrix factorization version of these DPFTRL beats DPSGD in all regimes. So any epsilon, it achieves the optimal trade-offs.
Nice, nice. The other question was a little more high level. So there's been a trend of using DP, the definition of DP, for problems other than privacy, but still in the broader regime of responsible AI or something of that sort. For example, machine unlearning is a variant of DP. More recently, copyright protection proofs are based on DP. Do you see any specific problems of that sort in the LLM era where DP and its variants could be a motivator to start with?
Yeah, in fact, there's a lot of data on the web that is possibly protected by things like GDPR's right to be forgotten. And therefore, if somebody puts something on the web and then later on decides that I want to remove this Stack Overflow post or this Twitter tweet or whatever it is, how do you do that? Sometimes the people that are scraping the data off the web aren't the ones that can receive that request. And so there is possibly some case to be made that even the foundation model itself should be trained with something like differential privacy. Maybe not exactly differential privacy, maybe we can debate and discuss the epsilons, but we should do something to make sure that it has not memorized, overfitted to anybody's user information.
Sure, yeah, fair enough, that's a good point. Yeah.
Thank you, Peter. Very nice talk. I'm glad to hear that federated learning is here to stay because I use a lot of it and in smart city applications, but also in trying to introduce differential privacy. I mean, the last thought you had there is to, because you're going to use large language models to train on the device, and that's, of course, the device is not enough, and resource constraints and so on. I read a few recent work on split learning, for instance, where you train the most important part of the data on the device and the rest on the server, and a few other ideas. What's your take on that, please?
So yeah, I mean, I'm arguing in this oh, I think they took out the slides. So yes, I think that we could train smaller models on device, and then these could be smaller generative models. We can train them with federated plus DP technologies, and then take that generative model, generate synthetic data, and use that into the training of the foundation model if needed. It's unclear to me if user data is going to be useful for those foundation models, but definitely once you start customizing the model And going into a specific domain, you need that data. You need to access it in order to get that improvement in accuracy. So yeah, I'm very much pro that, and I think the discussion right now is how do we do it? Do we use trusted execution environments to train with federated type techniques inside of them, or we continue to do it at the edge? Memory trade-offs, compute trade-offs, all that stuff kicks in, and we need to study that. Thank you.
Hi, Peter. I have another quick following-up question. So you talk about the fine-tuning stage is more for personalization. So could you please comment on the value of doing federated learning in this personalization or fine-tuning stage?
Yes. So as I said earlier in the talk, I think these big models that are trained on a lot of data have demonstrated that they have a lot of zero-shot or few-shot capabilities, and that helps because now we don't have to run a federated training algorithm for days and weeks, which we would have traditionally needed. Now we can actually do just a few rounds of training. So it speeds up the fine-tuning stage with federated technologies drastically, but it's still needed. Without that user data or in-domain data, we would not be able to achieve state-of-the-art accuracy and continue to improve performance on these variety of benchmarks, especially I think in the medical domain or in specific domains where we need user data. So I think it's needed. I think it's necessary. We can't just do zero shot. But I also think that the zero shotness or few shotness properties can help us speed things up. We need less training and less data. And so that's actually good because we don't have to wait for days and weeks to get that model. And that's something that engineers did not like about federated learning because it slows down the pace of research and development.
Okay, I'll ask the question. Thanks for the great talk. I want to touch upon the last topic that you mentioned about TEs and more specifically about TEs on accelerators. So, okay, we've seen Intel SGX and so on and so forth, but we're only tapping, I think, with the H100s now that they are supporting some kind of enclave in a GPU accelerator. Now TPUs, I don't think that they do. How do you see this sector evolving?
Yeah, I think first of all, a lot of us here are not hardware security researchers. A lot of us are algorithms, stats, information theory people, right? So I would love for the community to have some sort of a mathematical model for what a TEE is. What are the threats, surfaces of attack? We've probably all heard or seen these side channel attacks, correlations between the data and timing analyses and things like that. For researchers that are designing algorithms, figuring out precisely what the constraints are in terms of, can I just run arbitrarily any algorithm inside that box, any training method, or are there compute and memory constraints, and how do I capture those constraints into the design of some optimal algorithm? There's a lot, I think, that's open in that community. So far, we've just treated them as magic boxes. We can run anything in them arbitrarily, and nothing will go wrong. But a lot of things can and do go wrong. So we need these threat models, mathematical models to capture constraints and then design algorithms that are tailored for them. And so we're in the very early, I think, days of TEs.
Let's thank Peter.
Thank you.
So we next have Emmerich. Oh. Emmerich, I'm not going to pronounce your last name.
That's okay. Dieu le veut, French. But you can say it as ever you want. Don't do the long one.
Emmerich received his PhD in mathematical statistics from ENS de Paris in Ulm. And after this, he was a postdoc at EPFL, where he was a friend. Now he's a professor at École Polytechnique since 2023. His research is in high-dimensional statistics, optimization, statistical ML, and federated learning. His work covers both theory and also more applied work in collaboration with industrial partners with EDF, Accenture, and Oken.
Is the mic good? Yeah, seems good. Okay. Yeah, perfect. Okay, so thanks. First, I would like to obviously thank the organizers for having me here. And it's a great workshop. I love that we have been having like both very high-level talks, which are amazingly insightful, and some more technical ones. As part of the French team, I guess I'm going to be on the technical side of things. And I couldn't thank Peter enough for like his introduction, because actually what I'm going to present is very inspired by work of his team. That is one of like the biggest chain of influence in discussing the links between compression and privacy. Is what I'm going to talk about. And I mean, obviously, what we do is kind of a tiny building blocks in that direction of trying to have efficient federated algorithms that include some kind of privacy guarantees or other constraints. So this I should start by saying this is based on work with Mahmoud, who is a PhD track student in my team, and Remy, who is postdoc, both at École Polytechnique, so my bad, and CT Lee, who is at Chinese University of Hong Kong. And obviously, I thank them a lot for this collaboration, so it was super nice to work with them. So I'm going to skip the slides on all the details, but actually I'm not going to need any of the notations, but obviously we are working in that federated learning framework in which we have an average of n functions that we would like to optimize. And basically we don't need too much of the technicalities here. We have seen that graph several times. The starting point of most of our research is we want to keep the data locally, then we need to exchange with some central entity. And if we do that, the simplest thing to do would be distributed SGD. That's great. The problem is that then we communicate a crazy amount of information, which is problematic both from the privacy sides, because for communicating that much is going to leak a lot of information, and from the communication side, because communicating very large dimensional updates, a very large number of updates times, with a very large number of clients is not possible. So how we tackle that? We tackle that in two ways. We tackle that by communicating only a fraction of times. That's called local iterations. Or we could tackle that by communicating a fraction of weights. That's called quantization or projection, let's say. Low precision updates, that's called quantization, or with a fraction of workers. That's called subsampling. And so basically the good thing is that the last three here, the communicating with fraction of workers, fraction of the weights, or low precision updates can all be framed into one framework. It's called compression. The other one is called local iterations, like say, for example, federated averaging that Peter just talked about. And basically, these two things are extremely connected in how they behave. I'm not going to talk too much about that. I'm just going to briefly mention that we are interested in compression because it enables to tackle those three aspects, like fraction of the workers, fraction of the weights, or fraction or low precision updates. And the field has been extremely active in that. I'm just going to try to summarize 6 years of research, going far beyond my own, including some from people in the room. Edward, so several people have worked on that. And basically what people end up doing is say, I'm going to put an assumption that encompasses all those three compressors. So let's say it's unbiased, maybe, oops. That's, maybe you can switch back to full screen, or I don't know if I need to do that myself. Yeah, that's okay. So maybe we do something which says that all those compressions can be unbiased and have a bounded variance, and then we do stochastic gradient descent with those analyses, and things go well, or we do contractive operations. We ensure that, let's say, if I only pick the largest coordinate, I'm going to be closer, closer to the initial vector than the scale of the initial vector. So that's all great. And basically, I would say that there are two main takeaways in that for people that don't know this literature. The first one is that there is a trade-off between compression, how much I compress, and heterogeneity, very much like there's a trade-off between heterogeneity and local iterations, and we have similar algorithms to what Pranit proposed with scaffold, where you actually have to control and choose some kind of control variance to limit the impact of heterogeneity. So this was one line of work. And the second line of work, again, this is really community work, including some of my own, but not majority, is feedback loops, is that when you do compression, you do observe the gradient before compression and the compressed version to transmit. So if I transmit to Pranit a compressed version of my gradient, I can remember the difference, and afterwards I can keep that difference and propagate that back. So these are like two of the fundamental ideas that influence the community, and now we've tried to build upon that. And obviously this is connected also to what Peter mentioned at the end, that we can introduce noise that is correlated over several iterations, and I think there are like still a couple of interesting directions in that field. Okay, so what comes next? What I'm going to talk about in this talk is different things. I'm going to want to try to say that we have to go beyond that kind of worst case assumptions on compression operators where we put all of them in the same bag. Because actually, they are, like, if you try it, it actually doesn't behave the same well, the same as well for two compression that satisfy the same variance upper bound. So we have to work on that. Obviously, one I don't think I will have time to talk about. The second one, which is like trying to just show how different compression operators result in different convergence rates in what we do best, which is linear regression, so high-dimensional linear regression, and trying to see what exactly the rate is and how actually the, let's say, the regularity of the compression influences. So in one word, when you do quantization, you actually have that the compression of x and y, which are very close to each other, is much further than x and y, so on average. So this is something which is of interest. And what I'm going to talk about today is trying to do compression operators that produce a specific error. So why do we do that? We do that because, for example, we may be interested in producing a Gaussian error. And if I'm able to do a compression of x, which is exactly x plus a Gaussian noise, then maybe I can have some applications almost for free. So for example, let's say I want to generate DP noise, which is Gaussian noise, and I'm just able to compress my gradient, and it results in the gradient plus the noise. Then in some sense, I get the compression from free given a particular DP. And that's basically, I think, the most important application. The two other applications we could think of, and then there are many other ones, is Langevin dynamics. So for example, Alain presented a paper yesterday in which when you do federated Langevin, you end up, if you want to do compression, compressing your gradients. And afterwards, you add some noise, which is the Langevin noise, which is, again, a Gaussian. And you could just do that, again, for free. I mean, if you know that you are going to add Gaussian noise, you can get the compression for free. The constraints are a bit different because here you don't actually care that the noise would be not revealed to anyone. We're going to see it's a bit harder in the DP case. And the third one is randomized smoothing. So, I mean, say I have my own model, I'm the central server, I compress it before passing it to Mike. And that means that Mike receives a model which is my model plus a Gaussian noise in that case. And it means that when I'm doing the gradient descent or stochastic gradient descent, I have something like that, update WT plus 1, which is WT minus the gradient of f at the random points. And this is known as randomized smoothing. And if we have density on the noise CT here, the convergence rates are typically, I mean, easier, or at least we get smoothing on the function. So non-smooth function, this is actually the expected gradient of the smooth function with a smoothing kernel, which is with respect to the noise C. Okay, so there are several applications to have in mind. And these are the main motivations. Great. So I'm going to try to show you how we can do that. And actually, there's one key idea. Okay, so first, more related work on DP. I've said I need to give all the credits. So first, the high-level intuition is that DP and compression are clearly allies. If I compress drastically, I mean I say nothing, I'm extremely DP, right? I mean, I don't provide any information. So we clearly go in the same direction. I say that like, the first line of work is the one by Peter, and I think, I mean, obviously he's the expert in the room on the topic, but what's my understanding of Peter's work is that we try to see what utility we can achieve with epsilon delta dp, and then we create a compression operator that does not degrade that accuracy. And we try to find, okay, he's nodding in the right direction, that's good news. And we try to see that we can have an optimal complexity not to degrade the conversion rate. And then there is a second line of work which is very important, which is trying to do quantization, which means we are going to work on discrete sets, but instead of compressing on, let's say, 0 and 1, I'm going to discretize on all possible values of z and prove DP on that. It's a line of work by mostly people in Meta. Okay, and our approach is here focusing on what we call subtractive dithering, which is going to enable us to get specific noise. And as you can see, it's not a very complicated approach, but there are some things to take out of it. So we're going to focus on like producing a special noise. In fact, any unimodal noise is possible. We can do Gaussian, Laplace, anything. But I'm mostly going to talk about Gaussian because it's easiest to think about and the one that has the clearest applications. And okay, we're going to get DP with respect to an external observer if we have a trusted server, or we're going to get DP, we're going to get secure aggregation with respect to the server, or homomorphic encryption. Great, so let's move to the technique. So that's the one slide I want you to focus about. How do we get noise that has a distribution? And the key for that is, sharing a seed for randomness generation. So the most classical quantization technique is dithering. We take a vector x, and I transfer x to either 1 or 0 with probability x, which means that this has a distribution which is a binary of x, and the worst case error would be 1/4, the average case error if x is uniform is 1/6, and all is good for me. But now this is a discrete error, obviously, b of x. I either have an error of 1 minus x or x. Now what we're going to do is subtractive dithering is take the same x. We're going to first add some noise, u1, uniform noise between -1/2 and 1/2. So this is representing now my distribution in green. Try to create a color scale. And instead of doing quantization, now what we're going to do is project to the nearest neighbor. Okay, so it actually corresponds to projecting all the points right from this 1/2 line to 1, and all the points left to 0. And now that I've done that, okay, I can resplit my noise into the blue part and the red part. And what I'm going to do is to transmit that 0 and 1, which is the encoded vector, and then subtract the noise. So I mean to be able to access this uniform noise on both the sender and the receiver, meaning that I generate them simultaneously. And so if now I subtract this noise in red, which was going from -1/2 to -0.2, say, to 0, it means that I'm adding 0.2 to 0.5. Okay, so you see that it reverses, obviously, the order. And if I do that to the second part, then obviously I recover that I get exactly x plus minus 0.5 uniformly. Okay, so this is what subtractive dithering is. It exists since the 50s, in fact. I mean, it was applied first in signal processing as anything, ask Eric. And the good news is that we get uniform noise with average error and maximal error of 1/12. So, okay, and you see I've tried my best to align the graphs to the small screens. So I spent part of my night on that, so I just wanted to point that out. It's very important for me. I'm happy that it worked. Okay, so now what do we aim for doing? I mean, formally we need to define a framework, and what we're going to define is a framework we call IANQ, meaning we want to achieve additive independent noise quantization. So meaning that whatever the input is, x1 to xn, we want that the output of our framework minus the input is just a noise q, which is sampled independently from x and y. And so again, as I've said, we're going to use a shared randomness S, and we sample this shared randomness simultaneously on the sender and the receiver. We encode x depending on S, and we decode the encoded version depending on S. We call M the message, okay? E is the encoder, D is the decoder, M is the message, which is always going to be on a limited precision set. And subtractive dithering is just like exactly what I've described. For any input, you sample a uniform noise between 0 and 1, and you take M, which is the floor of x plus u. This is the same thing as taking x plus 0.5 to minus 0.5 and taking the nearest neighbor. It's just like easier to rewrite. We decode by taking m minus u, and then we get exactly what I've said before. And obviously, I can do that. I can also do that with a multiplicative factor of w, and then I get a uniform noise between minus w over 2 to w of 2, and just multiply everything by w. So now how can we create Gaussian noise? I mean, basically, we're going to say that the Gaussian noise is just a mixture of uniform noises, and I'm going to first sample uniformly one length according to the distribution of the lengths of those uniforms to get the Gaussian noise. And that's something I can generate simultaneously on the sender and the receiver. So I'm generating, let's say, that FD, which is basically follows the distribution of that particular length. So, okay, I don't want to get too much into mathematical notations, but basically, I look at the distribution of the length horizontally of that uniform with respect to points, sampled according to a Gaussian noise. And if I do the mixture of my uniform noise, I exactly get the Gaussian noise. So, okay, this is called the layered quantizer. And the problem is that typically the length of the codebook, when I have very small parts here, the length of the codebook tends to explode. Okay, and this scheme was proposed by a paper by Mahmoud and CT earlier, a year ago. And so when the length explodes, because here to get this very small noise, I need to divide by D, which is very small, and divided by D very small makes my support very large. So you can fix that, in fact, by doing what's called shifted quantizer, and I'm missing a picture, unfortunately, so I won't explain it too much, but what you do, in fact, is to revert 1/2 the negative part of a Gaussian, to flip it, and when you flip it, it makes actually the length of any band positive. Sorry for the missing picture. And then you can ensure that the code size is uniformly bounded, so you have good news. So then we do theory, because we like to do a bit of theory. Obviously, this is our goal in life. So we show that basically for that, you can get both lower bounds on what you could achieve in terms of entropy, which corresponds to the minimal length of the code that you could achieve, which is the entropy of M, your signal, a message given your shared randomness, obviously, and you have basically nearly matching upper bound and lower bound, so I won't get too much into the details, but you feel that you're not doing something too bad. Okay, that's just verifies the upper bounds. So now what's our problem? That's the last thing I want to convince you about, is that when we do that in an aggregated framework, basically we don't get DP, with respect to the server at least. I mean, the server could aggregate everything and transmit that, and we'll have purely noise. But otherwise, the server receives our shared randomness or sees the shared randomness. So it can subtract the shared randomness and recover our message or information on our message, which is like the quantization of our X plus noise. So in order to get a stronger guarantee, what we want to do is to be able to average all the messages before decoding. And this is what we called, it's called homomorphic case. I want the decoder, oops, again, sorry, my bad for that. I want the decoder and the encoder to, the decoder and the average to commute. So that I can first aggregate my end messages and then only pass that to the central server, and maybe I can do some extra steps in that, and then I decode the average. And if I do that, I'm very happy. But can I do that? The problem is that if we just look at what we have done before, and I think I'm nearly out of time, so I'm going to be quick. If we look at what we've done before, basically we're sampling a length uniformly. If we do that on all clients, we get that each decoded message is going to be xi plus a Gaussian noise. Obviously, we can average those, and the average of the messages would be exactly my target plus Gaussian noise. But clearly, I don't commute, and the reason why I don't commute is that I have this di scaling factor here, and basically di is different for everyone, so I cannot average the messages mi and subtract the average of that, because di is not constant. So I need to, in some sense, fix that in order to be able to aggregate before decoding. I want to have a fixed constant here. That's exactly what you can do. So you say, instead, I'm going to have a shared randomness t, which is this t, and we all select a uniform noise. We do the same scheme, but with fixed t for all clients. Now we all have the same scaling factor, and because we all have the same scaling factor, we can aggregate and then decode instead of decoding individually. But now the noise that we get is clearly not Gaussian, because each of these variables is conditioned to t is a uniform between minus t over 2 and t over 2. And so the average is not Gaussian conditioned to t, it's actually what is called an Irwin-Hall distribution. It's a sum of uniforms. And that's at first a problem, because conditionally to t, I don't get the Gaussian distribution that I want, but now I can just do a mixture on t again. So I need to decompose a Gaussian of any given parameter sigma squared as a combination of Irwin-Halls that corresponds as the sum of n uniform noises between minus t and t, for t being a random variable. And so that's just what we want. We want exactly that the sum of these decoded messages that are those Irwin-Halls is basically q. And just, finding such a decomposition is a very simple rejection technique, and then we get, ultimately, that we get exactly what we want, which is our A, and Q aggregated homomorphic mechanism. And I think, okay, we can again do theory on that. I'm not going to do that. And basically, I just summarize the theory is again trying to provide control on the number of bits you have to transmit. And then I can summarize the different schemes you could get, basically starting from direct quantizer, the shifted one in which I reduce the maximal number of bits, then Irwin-Hall. Irwin-Hall is being neither DP nor Gaussian noise. So neither actually something you can do Rini DP on, at least. Then aggregate Gaussian, and then you can do subsampling on that in order to match as closely as possible what Peter has done. And yeah, that's the conclusion. We're trying to find a way to generate a specific noise distribution. I think there are still directions to explore on that. Personally, I hope that we can do something that improves optimization when we choose the noise distribution, but this is up for debate. Whether there's something more than just the squared noise, the squared moment of the noise that matters. And we have controlled communication cost and applications that I already mentioned. Thank you very much.
Thanks so much. I see you.
So thanks a lot for focusing on the construction and the technique, but I think the slide that you skipped is actually important. So how does that improve on the other schemes?
The ones you have, for example?
Let's see.
Yeah, in some sense, it's just saying that if my understanding is correct again, what you show is, say I want to do epsilon delta dp, can I add, can I do some kind of compression that doesn't decrease accuracy? And what we say is that, say you want to do epsilon delta dp, what is the budget you can do that for free? Now, if your budget is bigger than that, communication budget, then I can reduce it. If your budget is lower than that, I can do epsilon delta dp with better parameters epsilon delta than you did. So in some sense, either your budget was larger than the one I had, and I can reduce it and do the same epsilon delta, or it was smaller than the one you had, and I can improve your guarantee. So it's just saying that we can have something that is tight. And then we can do it on coordinates if we have the trusted server, a bit like you did. Okay, there are a few things we could discuss. I think that goes into the deal. Okay, so and I had one image on that, but unfortunately it's very far in the slides, so I need to rush in the bonus slides, which is basically say that, okay, basically if we compare to your scheme, we don't gain much. We gain something like a factor of 2, typically on the variance of the gradient. And we gain that little when we are in the regime in which we do subsampling. You know, if we're in the regime where D is small and we don't do subsampling, then we gain much more. We gain something like a factor on 4 to 8, I think even sometimes a bit like 16 on the number of bits. So that depends on the regimes. In the regimes where we really want to be in n epsilon squared or n squared epsilon squared and not D, we gain a factor of 2. Otherwise, we can gain something a bit bigger, like 16.
While Alexei is setting up his laptop, maybe we can take one final question if there's anything. Otherwise, let's thank Kepnik again.
Thank you.
Guys, can I have help with the mic?
So we next have Alexei Tumanov. His talk will be one of the keynotes today. So he's an assistant professor of computer science at Georgia Tech. He directs the Systems for Artificial Intelligence Lab, SAIL. The research agenda of his lab is to build distributed systems which support real-time machine learning, training, and inference. So given that all these models are growing so fast, and we're all sort of very curious about how to make them more efficient and get them to actually train on the edge. So I'm curious to learn more.
Test.
It's not here. Can you put it on screen? Because I don't see it. Yeah. Let's see where it is. It's not here.
What are you looking for?
I want to take this out.
Maybe you minimize that. Yeah, click on this bar and move it to the top right. Top right. Yeah. And then maximize the screen again. Okay. Good morning, everyone. My name is Alexei Tumanov. I'm going to be talking about federated learning for multi-capacity DNNs today. Is everything okay? He's giving me this look like something is not okay.
Oh, you want this behind the ear. Okay, I see. Test. Yeah. Good morning. We're going to be talking about federated learning for multi-capacity DNNs, or as advertised, cost-efficient federated NAS for on-device inference. My name is Alexei. I come here from Georgia Tech. I work on the intersection of systems and machine learning. So first of all, what I would like to do is I would like to build the intuition for why we care about multi-capacity DNNs. As we all know, machine learning applications are increasingly deployed in dynamic and unpredictable conditions. And in such situations, what we have is that more and more we care about both latency and accuracy at the same time. Both of those constraints are critical. Furthermore, machine learning applications are increasingly running on resource-constrained devices that are forced to choose between accuracy and latency because you don't have abundant compute in all cases. And that, in addition to this, what's complicated is that it must be done rapidly in order to avoid missing deadlines. So let's take a look at this toy example. This example is sort of drawn from the cyber-physical systems, in this case an AV car. You have a car that's, for example, navigating through an urban terrain, a lot of things going on. You have to predict, or basically you have to perform object detection on the street, on the street signs. You have to perform classification for the objects moving on the road. And in order to avoid the collision, you have to make the decision really, really fast on the left-hand side. And so maybe to make sure that you actually satisfy this, this deadline, you could do that with a lower accuracy model. Whereas on the right-hand side, if you're driving through an urban terrain, the complexity of the queries is a lot less because the frames that you're drawing from the onboard cameras don't really have as much work to do, essentially. And so you have more time to make those decisions, let's say 20 milliseconds instead of 2 milliseconds. And so you can actually afford to spend more time on this compute at higher accuracy. So in one case, this example should motivate that in one case you might be willing to use something that is to the further left in the accuracy latency trade-off space, while in the other case you might be willing to use something that's to the top and the right hand part of this latency accuracy trade-off space. What I'm trying to emphasize here is that the important takeaway from this slide is that I don't think that the single point in this latency accuracy trade-off space is sufficient. While state-of-the-art focuses on optimizing for a single point in the latency accuracy trade-off space. So what we want to be able to do is we want to be able to train a family of models. We want to be able to train a set of latency accuracy options at the same time, cost efficiently. But the question is how? So I mentioned dynamic deployment scenarios at inference time. Let's very briefly talk about what are the sources of that dynamism. First of all, you have different hardware types. That one is a pretty straightforward and it's a pretty well-studied problem in the federated learning literature. But we also have variable traffic and latency constraints, and we also have dynamic resource availability, such as, let's say, this trace that was drawn from Microsoft Azure Functions. You can see that it's very spiky, and the spikiness is over a very large and wide range of throughput in queries per second, in this case from 5,000 to 9,000 queries per second. We also have to deal with the dynamism associated with how much power and energy you have left on the battery on the device where you're performing inference. Another motivation for federated learning has been pretty well studied, and of course, healthcare is a poster child for federated learning because of the privacy considerations. So why we want to do FL, one of the motivations for FL is to maintain the privacy of the patient data, right? So in this particular case, you have multiple hospitals. Those hospitals have edge clusters, and they have some private data they want to train over, and they cannot share that data. So basically, you have a secure cloud where you aggregate model updates, and you send the updated model to the individual hospitals to perform some local updates on the local cluster data, on the local patient data. And of course, another poster child for federated learning is the cross-device case where you have Gboard and the next word prediction task here that's operating in a very different regime across a much bigger number of clients with a lot more heterogeneity. And in this particular case, the model that's being trained is the next word prediction model. Okay, so here are some backgrounds and trends. Overall, what we are observing is that we have increasing and growing heterogeneity in the privacy-sensitive data and compute. So in terms of privacy-sensitive data heterogeneity, this has been emphasized in literature. For example, there's this Nature Medicine journal that published a paper on federated learning for predicting clinical outcomes for patients with COVID-19. The heterogeneity of data, extreme heterogeneity of data, is something they explicitly pointed out. And this is a cross-hospital study that was quite interesting from federated learning perspective. If you haven't had a chance, I encourage you to take a look. There's increasing heterogeneity in compute. You have to deal with all sorts of static and dynamic heterogeneity in terms of the bedside compute that you have, in terms of the edge cluster compute that you have. But there are also some newly emerging challenges that are quite interesting, that are much more dynamic. So the dynamic factors that I previously mentioned are query traffic, complexity, power levels, and latency deadlines. Okay? So here's a kind of an anchor slide. What is the goal of our work? The goal is to come up with privacy-preserving distributed training regime where we train once and deploy for multiple scenarios. And we take care of the static parameters, such as the deployment hardware, as well as dynamic parameters, the real-time parameters that change while your application is running. So that includes query complexity, power level, query traffic. The proposed solution, how the mechanism that we are trying to use for this is the weight-shared supernet training in federated setting. And the key takeaway is the following. What are we trying to do? We're trying to build, or we're trying to train Pareto frontiers with asymptotic complexity of order 1 in a federated fashion. Okay? Pareto frontiers per client in order 1 in a federated fashion. How are we trying to do this? The mechanism for this is weight-shared DNNs. Why do we care? Why federated? Privacy preservation. Why weight sharing? Is because it gives us the ability to produce this family of models instead of a single point that a lot of the state-of-the-art continues to focus on to this day. So just to reemphasize, we have federated learning state-of-the-art, where you have a server in the middle, this blue cloud right here. It actually basically sends the updated model to the clients. The clients are performing some local updates. They aggregate it back on the server with all sorts of bells and whistles. But fundamentally, at the end of the training, what you end up is a single point per client in the latency accuracy trade-off space. That's state-of-the-art. What we want to be able to achieve, as I mentioned, is a family of models per client. How do we do that? Well, the conventional approach would be to basically train a different neural network for every single different deployment scenario that you care about. And this is what you see at the very top. Clearly, this is very expensive, right? More recently, in a centralized setting, there was a paper in Ai Quorum 2020 that basically proposed weight-shared approach in a centralized setting that actually does give you a cloud of points in accuracy latency trade-off space. And the claim to fame for this paper is the separation of training from neural architecture search. They've performed training for this super network in a centralized setting, and then they extract they have the ability to extract subnetworks post-training without fine-tuning. We improved on that work in Ai Quorum 2021, where we basically improved the cost efficiency of this by focusing on training the points that we believe, using some heuristic, is closer to the Pareto frontier of optimality. Okay, so as I mentioned, state-of-the-art is centralized weight-shared DNNs. Weight-shared DNNs are obtained by adding elasticity to the DNN dimensions. The supernet is formed. It forms a comprehensive and a large model, and then subnetworks they differ in several elastic dimensions. They partially share their weights, and they can be directly used for predictions without any further retraining. So that last part is very important. And the weight-shared DNNs include a rich trade of space between accuracy and latency, which is what we wanted initially based on our initial set of motivation slides, right? So just a few words of how we, in terms of how we achieve this elasticity. Let's take a look at this residual network. It's typically constructed by stringing together a bunch of stages. Each stage consists of some number of bottleneck blocks. Basically, the way we achieve elasticity is by looking at the depth, width, the kernel, and resolution, and making them elastic. So just as an example, let's take a look at this. We have some n stages, and we have each stage consisting of 4 bottleneck blocks. So in this particular case, this is the maximum number of bottleneck blocks that you have per stage. And we have this D list that keeps track of how many bottleneck blocks we keep per stage. So the ith element of D corresponds to how many bottleneck blocks we have per stage. But we could also skip some of the blocks. So in this particular case, instead of the maximum number of 4 bottleneck blocks per stage, we have two bottleneck blocks per stage. We can also have everything in between independently across stages. And we have another parameter that keeps track of the multiplication factor that basically controls the width of the bottleneck blocks that are used for each of the stages. Okay, so this is just an illustration of how you would achieve different dimensionality in the subnetworks. At the end, what you get is a point cloud. On the x-axis here, you have flops. On the y-axis, you have test accuracy. And of course, what we care about is the Pareto frontier of this point cloud. In other words, for any given flop budget, we want the highest accuracy model, or for any threshold for accuracy, we want the lowest flop budget achieving that accuracy. Okay, so the top left is the best, and this is what we want to achieve per client. Right, so this brings us to the proposal. Superfed achieves this with weight-shared federated training. What we have is a server that keeps track of the super network, and the super network sends the subnetworks to the clients for some local update. And the critical difference here is on the right-hand side of the slide, where instead of producing a single point per client, at the end of training, what you achieve is a Pareto frontier. And that's the key qualitative difference. Of course, the first challenge to achieving this is subnetwork distribution. We have to think about 2 things. First is the spatial component. I call it spatio-temporal subnetwork distribution. The spatial component basically says which specific subnetworks are sampled from a supernet and which clients they go to for that specific round R. So that's the spatial part. The temporal part is that there's also temporal dynamics, the load balancing across time. Basically, what this keeps track of is over time, where do we send the minimum subnetwork, where do we send the maximum subnetwork, and in general, how do we load balance these subnetworks that was sampled from the supernet across clients over time. And so for the spatial, the way we sample this is what's called sandwich sampling. And what it does is it samples the smallest and the largest subnetwork per round, at the very least, and some number of subnetworks randomly sampled in between. And the temporal component is basically done by tracking the largest and the smallest networks that are seen by every client. So what we do is we assign the smallest network to the client which has seen it the smallest number of times. And so we have an illustration for this. Horizontally, you have time. Vertically, you have your clients. So vertical is the spatial dimension. Horizontal is the temporal dimension. You have client IDs 0, 1, 2. And we are keeping track of the maximum and the minimum network count that each client has seen. So during round 0, we send the minimum subnetwork to client 0 and the maximum subnetwork to client 2. So we increment the black and the red count. For round 1, basically what we did is we sent the maximum subnetwork to client 0 and the minimum subnetwork to client 1, and so on and so forth. So for every single round, we make sure that we send the minimum and the maximum subnetworks to the clients that have seen it the least. And this is the temporal load balancing component. Very simple, but very effective technique. The second challenge is, what do you do at aggregation time? Because now, instead of sending the same architecture to every single client, right, which is pretty homogeneous, and you just perform some sort of federated averaging at the end, you have variable subnetworks to deal with that are weight shared. You know, they're not independent, they're weight shared. And here's an illustration of this. So let's say that you sample the minimum subnetwork on the left-hand side and the maximum subnetwork on the right-hand side. So here, what this shows is a single stage that on the left-hand side consists of 2 bottleneck blocks with an expansion ratio of 0.1. On the right-hand side, it consists of 4 bottleneck blocks. So the dot, dot, dot here corresponds to the 2 missing bottleneck blocks. And the expansion ratio is 0.25. And each of these rectangles is weight shared across the 2 clients, okay? And so there are 2 different approaches to dealing with aggregation. The normal one is just sum it up and divide by the cardinal overlaps. Okay, so if for a particular weight it was contributed to by, let's say, 3 clients, then you sum it up and divide it by 3. If it's by 2 clients, you sum it up and divide it by 4, sum it up and divide it by 4, and so on and so forth. That's pretty straightforward. What we are doing is we are using the weighted average approach, where we favor the weights that are coming from a specific subnetwork more, and there are reasons for that. Okay, and so we aggregate overlapping weights with more weight assigned to the maximum network contribution. We account for variable cardinality of overlap, and on top of this, we decay basically this priority given to the maximum network, the max net weight, over time, using the parameter beta that's assigned to the largest network contribution. So what we do is we assign 1 minus beta over C minus 1 assigned to all the remaining C minus 1 client contributions. And the beta is decayed from 0.9 to uniform. Of course, this is a hyperparameter as the rounds proceed. And we can do the decay itself in various different ways. We've tried linear decay and cosine decay. Cosine decay performed the best. And so to summarize, the spatiotemporal weight shared FL training, it sort of consists of these 3 components. The first one is the subnetwork distribution, which includes tracking sandwich sampling, and it includes the temporal load balancing. And the second part of this is what do you do at aggregation time, which includes the decaying maximum network favored weight shared average. So, how are we doing in terms of evaluation? First, we tried this technique over a number of different data sets, CIFAR 10, CIFAR 100, and CINIC 10. And the setup here is that we used the Dirichlet alpha parameter of 100, which basically corresponds to pretty homogeneous data with client participation ratio of 0.4. And the number of clients for these 3 workloads was 20 for CIFAR 10, 20 for CIFAR 100, and 100 clients for CINIC 10. And basically the comparison here was with federated averaging, where each of the points that you see, each of the blue diamonds, was independently trained. So remember, the goal is for us to achieve a Pareto frontier per client, right? One of the mechanisms using state-of-the-art techniques is to train these different points on a Pareto frontier independently using state-of-the-art techniques. And the comparison is across the Pareto frontiers that you achieve, either using our proposed technique, which is in this case superfed, or using the state-of-the-art techniques. So higher is better, the orange is us, and we are outperforming independently trained federated averaging in all cases, and the performance is robust across different data sets and the different number of clients. Okay. Now, what happens if we change and vary the client participation ratio? With the client participation ratio of 0.2, 0.4, and 0.8. In this particular case, we set the number of clients to 20, and the statistical heterogeneity was mostly homogeneous. And some observations are that you can see across the slide is that we have an increasing gap between I-federated averaging and superfed with the increasing participation ratio. IFED average accuracy suffers from the greater client participation. We believe that the reason for this is the interference when you don't account for basically the aggregation of contributions from multiple subnetworks. Okay, so in terms of cost of training, because remember what we are doing is we're trying to do it in a cost-efficient way, we're looking at computational cost and communication cost. So for, on the left-hand side, we have computation cost, and as you can see, one of the goals from the very beginning was to make sure that the cost we're paying is asymptotically order 1. And this is what's seen here. No matter what the model family size that you have, right, the cost that we're paying for producing this model family size is constant. And that's a very good property to have, because regardless of the density of the Pareto frontier that you want to be able to achieve, you're going to pay a fixed cost for that. Using state-of-the-art techniques that don't have this asymptotic property, of course, you are going to have some sort of monotonically increasing cost function as a function of model family size. And this is exactly what you're observing here. And we stopped it at the model family size of 9, but obviously it's going to keep going, and the gap is going to keep spreading. And so from the perspective of publication, I could report 1 order of magnitude improvement in cost performance, 2 orders of magnitude improvement in cost performance, whatever you want, depending on the model family size. Here, we just stopped at the model family size of 9, and we demonstrated that even for as few as 9 points on the Pareto frontier per client, we're able to reduce the computational and communication cost by an order of magnitude. Okay. We also looked at the effect of data heterogeneity, because remember I mentioned that this is a big problem. So here, we're taking the following approach to data heterogeneity. So on the left-hand side, we're using the Dirichlet distribution in order to simulate data heterogeneity across classes and clients. So horizontally, you have the client IDs from 0 to 20. Vertically, you have the class numbers from 0 to 9, so 10 classes in total. And basically, the diameter of this dot corresponds to how much this particular class for this particular is represented on this particular client, right? And so as you increase this alpha parameter for the Dirichlet distribution, you're going to see an increasing heterogeneity in the diameters of your colored dots. And this corresponds to increased statistical heterogeneity, which creates a problem for most federated learning algorithms. Okay. So how are we doing with respect to statistical heterogeneity? So on the left-hand side, mostly homogeneous, alpha equals 100. In the middle, we have some heterogeneity with alpha equals to 1. On the right-hand side, we have alpha equals to 0.1, mostly heterogeneous. You can see that higher is better, orange is us, and we are outperforming the independently trained federated averaging. And in addition to this, we're also robust, or more robust, to the increase in statistical heterogeneity compared to federated averaging. So, in summary, where I started with is by saying that applications across many domains, including augmented reality, virtual reality, healthcare, machine learning for healthcare in intensive care units, they're increasingly dependent on machine learning, and they increasingly care about both latency and accuracy at the same time. And so for that reason, it stands to reason that no single model is sufficient to serve applications like this, even when you're running a single application running on a single device. So one application, one device, I argue that you want a Pareto frontier even in that particular case, okay? Because of all of that dynamic heterogeneity that's happening. So what that means, sort of by implication, is that we need to be able to train a family of models, and we need to be able to do that cost efficiently, of course, while preserving the privacy of the data. So what we have proposed is we've proposed one mechanism to achieve this, and that's called weight-shared federated learning. And our contributions to that are twofold: the spatio-temporal subnetwork distribution, What that means is that you make a decision which subnetworks to subsample and which clients to send them to for a given round R. And you load balance that over time. And the second component of the contribution is what do you do at aggregation time? Basically, how do you perform model parameter aggregation with arbitrarily variable overlap? The takeaway results is, as I mentioned, I can put any order of magnitude here depending on the density of the Pareto frontier that your application cares about. Let's just pick one, order of magnitude savings in compute and communication cost. We are matching or exceeding state-of-the-art accuracy, and we are robust and generalizable across data sets, client participation ratios, and heterogeneity levels. On that note, I would like to conclude. Thank you, everyone, for your attention, and open it up to questions. And I would like to keep the slides on.
Hi. Thank you so much for the presentation. Just a quick question. So I want to ask about the convergence in terms of the global rounds required. So your method versus the independent Fed average. So how many rounds are required? What is the impact? Because we are sampling and then sending it to independent clients. So what does that affect? How does that affect the global rounds required?
Both were. So first of all, we didn't do theoretical analysis, so I don't have anything to say in terms of the theoretical guarantees of convergence. From the experimental setup perspective, we used the same number of clients, same number of rounds for both.
Thank you.
Yeah. Yeah, because otherwise this would have been reflected in the cost calculation. Yeah, so we wanted to make sure that the cost calculation is fair and apples-to-apples comparison.
Hi, Alex. Great talk. Thanks. One question is on the sandwich part that you mentioned. And during partial, so you assume partial participation with different participation rates. During federation, do you assume that you always have a client that can run the maximum model of your supernet?
Yeah, that's a very good question. So. From the perspective of this presentation, yes, that is the assumption that is being made by the algorithm. However, we can relax that assumption because all we care about is 100% coverage for model parameters. So basically, for any given round, the invariant that we want to be able to sustain is that every single model parameter has been sent to at least one client. One way to do that, in a very simple case, is just sample maximum network, because then you're guaranteed 100% coverage of model parameters. But you don't necessarily have to do that, but then that complicates the sampling procedure, right?
Yeah. Thank you.
Yeah. That's a great question.
Right. Hey, Alexei. So,
hey.
Nice talk.
Thank you.
One question I'd like to ask is, in your premise, right, you talk about latency, sensitivity in various domains, and I think we agree that's usually thought of as an inference time question. Mm-hmm. And here you're talking about basically the how to train this family of models. That's right. And so have you considered what happens when these devices that are training models, right? Do you envision that they are performing training at the same time they're using resources to perform inference? And if what's the case, then how does the fact that these federated devices are performing training, how does that compete? How can that be balanced against the set of resources that they need to use for inference? Does that require them to store the full family of models on each device, or they're going to be stuck with whichever, sandwich layer of the model that you've given it, right? So these are the questions that pop in my mind, the relationship between training and inference, and what happens when they're occurring on the same device, as I seem to be reading from your setting. Mm-hmm, mm-hmm.
Okay, I think I'm still on the mic. Okay, good. Yeah, that's actually a very good question. In some sense, sort of the resource management aspect of this, when you're running both at the same time, is orthogonal to this work. But given that we are focused on both inference and training here, it's definitely something that we're thinking about in a separate project. It's a great question. It's subject to open debate and open research. You could imagine different kinds of approaches to this, like for example, performing statical partitioning of the resources that you allocate for training and inference, especially in the case where inference is trying to maximize latency SLO attainment. You want to make sure that you're operating within some predictable resource envelope. And then sort of the rest of the resources that you have available, you can allocate for the purposes of training. This is slightly sort of less fulfilling for us from the SysML domain. Especially given the fact that over time you're sending different sized models to different clients, you can definitely take advantage of that. And so whenever you receive a certain sized model, you can reallocate the remaining capacity of the device for the purposes of inference. So that's actually, I really like that question, because you can transiently and intermittently increase the serving capacity of the device depending on what size subnetwork they actually have to train at any given round.
Right, and you saw where I was, you got where I was going with that question, right? Because then the question becomes, does that open new opportunities in the policy by which you send subnetworks, right? Right now, it's essentially kind of like fairness-based, right? You want to make sure everyone's seen the maximum and minimum subnetworks a certain amount of times, right?
Yeah.
And then, as we all know in scheduling, right? Fairness is the antithesis of
performance.
Of fulfillment, exactly.
Yes.
So once you start enforcing fairness, what happens to the devices that I got a latency problem, I need to get this now on my self-driving car crashes, as in your diagram, right? Then you start getting all the really interesting questions in scheduling, right? So I thought it was pretty cool to think about that.
Yeah, and it actually goes both ways. For example, if for this particular worker, I have a queue that's building up with queries, so I know I need to transiently increase the serving capacity of that particular worker, I'm going to communicate a reduced capacity for the subnetwork size that I'm able to receive at this federated round R. And so, that can be propagated to the server, and the server will honor that transient capacity constraint.
Right.
And so what you're essentially doing is you are sampling the subnetworks on the client side within the time variable envelope of the client capacity, of the client model size capacity. And what's interesting is that our mechanism of subnetwork sampling actually allows for that. So notice that if we are constantly sending the same kind of model architecture to all the clients, it doesn't have that flexibility. And so we left it outside of scope for this particular work, the dynamic training time heterogeneity on the client perspective, but this plays really nicely with training and inference overlap workload.
Right, it makes sense, right, with the fact that you're stochastic about how you send things to, devices means that you can tolerate up to a certain amount of unfairness without becoming grossly unfair in a way that disincentivizes the participating devices.
Yeah.
Cool. All right, thanks for answering the question.
Yeah, thank you. Great question. Anybody else?
Yeah, let's thank Alexei.
Yeah. Thank you.
So we're unfortunately running a little bit more delayed than usual. So it's going to be a relatively short coffee break. Maybe I'll see everyone in about 10 minutes. See you soon. it away.
Okay, it works? Yeah. Okay, yeah. So thank you very much for your invitation and for an opportunity to give a talk here at this nice workshop. So I need to apologize first. Probably it will be the least federated talk of today, but it will be rather on some more fundamental aspects of optimization with Markovian noise. Which yet covers some interesting specifics, which also arises in decentralized optimization, in different privacy techniques, and also in the federated learning. So my today talk will be based on our joint work with Alexander Beznosikov, with Eric Moulinet, and with other team members from our Russian HSC team, with Alexander Gasnikov, with Alexei Naumov, and with Marina Sheshukova. So this paper is accepted to the CNU RIBS. So the general problem that I will be talking about, so okay, it is a standard minimization problem. We have some function f of x, which is an expectation of some oracle function large f. You don't have access to large f, you don't have access to the gradients, you don't have access to the function small f itself, you have access only to large f and to its gradients. And contrary to the ID setting, we don't assume that the noise variables are sampled independently, so it is time homogeneous Markov chains. And there are quite a lot of examples where this type of problem appears. So you can assume, for example, the kind of token algorithms. You can think about Markov chain SGD or its differentially private versions with additional additive noise in the gradient. And in general, you can think about the setting of decentralized optimization as maybe the routine of primary interest for this type of results. So the main ideas that we will talk about are the following. So we provide kind of uniform framework which allows to cover both the setting of strongly convex optimization problems, non-convex problems, and monotone and strongly monotone variational inequalities, based on a simple idea of using randomized batch size. So apparently this idea falls nicely into all mentioned frameworks and allows to obtain theoretically optimal results, at least in the worst case, optimal. So we will put some standard technical assumptions. So the problem is L-smooth, mu strongly convex, at least for the very beginning. And from our noise variables, we will assume that the sequence of noise variables Zi forms the time homogeneous Markov chain, which we will assume to be uniformly geometrically ergodic. And moreover, we will need to impose some additional condition A4, which is also quite classical in the optimization literature, but typically when you speak about independent noise setting, it resembles the strong growth condition, and it allows us to somehow control the noise which comes from the gradient oracles. And the general idea that we will present, so I will not get too much into the technical details presented here, but the main idea of all the three frameworks, which allows to obtain tight, theoretically optimal guarantees, will be to use the batch size, which scales actually with a sample from a truncated geometric distribution, which is appropriately rescaled. by additional parameter which corresponds to the batch size large B. Apparently, this parameter large B will be of primary importance. You can think about this scheme as somehow about something which is also inspired by a multi-level Monte Carlo, because you see that when you account for the stochastic estimate of the gradient, in this case, you use the previous sample estimate as kind of control variate, which allows you to have a kind of nice telescopic property of the estimate. You will show that this technique is extremely useful to dramatically decrease the bias of the stochastic estimate, and at the same time to have only quite moderate payment in the variance, apparently. Because of course, when you work with Markovian type of optimization, and if you run the recurrence, you start to count the k+1 step error in terms of k step error, and apparently when you take a conditional mathematical expectation, you will no longer have unbiasedness property of your gradient oracles, contrary to what you have in the IAD setting. And that is the main challenge, and this bias can be exactly reduced by the proposed randomized technique. In the non-convex setting, it appeared previously in the ICML submission 2022 by Dorfman and Levy, and here we somehow generalized it. What is the main feature of this technical idea, if you wish? You see that if you scale the maximum batch size with a constant which is large M, you can decrease the bias quadratically with this parameter M, and at the same time you pay only logarithmic factor of this parameter M for the associated increase in variance, which is a very nice trade-off and allows you to balance the two sources of error somehow. Then we can have some results on the sample complexity of the, first of all, of the optimization problem with strongly convex constraints. And if you consider the strongly convex setting, our sample complexity bound that we proved with this randomization technique, it matches the results which are known for the case of independent noise setting up to the multiplicative factor of the mixing time. So basically, it is exactly what you should expect for when you start to do optimization with the Markovian noise. And apparently, we will show that you, in general, you cannot do better until you put some specific assumptions, some more specific assumptions on the problem. And this phenomena is already known because, for example, if you deal with regression with Markovian data, then you have very simple algorithm, which is SGD with data drop, which can be shown to be optimal for this setting. And apparently, you cannot do much better than just skipping than just taking every tmix iteration of your chains and proceeding with some update and then continuing iterates. And basically, our results shows exactly this. At the same time, it is the first analysis of the strongly convex optimization problem with the Markovian noise, which allows for both the optimization and noise terms, which scales linearly with the mixing time. So before there was a gap in the literature in this direction. And we can show that our result is apparently tight. So basically, we can show that the presence of the mixing time is not an artifact of the proof, first of all, neither in the variance part nor in the optimization part of the noise. And the only thing which is maybe not tight in the previous analysis is the dependence of our sample complexity bound on the constant delta squared, which comes from the strong growth condition. It is also not an artifact of the proof. We can provide a respective example, but nevertheless, the dependence on this condition number perhaps could be improved in the upper bound. So here it is just a table to show that exactly our result matches the sample complexity for accelerated SGD up to this additional multiplicative factor of mixing time. In fact, so I will just skip this slide. In fact, if you switch now to just convex minimization problems, then you can come up with a simpler version of the algorithm, just for a randomized gradient descent, which allows for the same randomization scheme. Now, previously, the algorithm that we considered was a modification of Nesterov accelerated gradient. Now it is just simple SGD with randomized batch size. And apparently, if you apply it to L-smooth problems, so either convex or even not convex, so you completely remove A2, you can show that the resulting algorithm is minimax optimal. And again, it has exactly the same sample complexity as the one which is the one which corresponds to the independent noise setting up to additional mixing time factor. And again, so the corresponding bound for IID setting was of course already known. And moreover, what is also nice about the proposed technique is that you can do exactly the same. So you can trace the same stochastic gradient estimates for the stochastic extra gradient algorithm, which is kind of natural and optimal counterpart of either accelerated gradient descent or just gradient descent for the case of variational inequalities. And if you switch to the example of VI, if you switch to the example of VI, then basically you can think about them as a kind of minimax problem with approximate convex concave function G and a couple of convex functions R1 and R2. You can show that basically having these same assumptions, which duplicate the L-smooth and strongly convexity assumptions from the minimization part of the talk, you can have, okay, I will show the results only for the monotone VIs in this case, achieved with the randomized extra gradient scheme. Introducing the standard gap function as a measure of the performance of the algorithm, we can show that we have a sample complexity, again, which is linear in mixing time, which is the first result of this type in literature. And moreover, we can show that, again, it matches the results which are presented in the IID setting up to these additional mixing time factors. Similarly to what was presented before in the optimization part, you cannot do better unless you put some specific additional theoretical assumptions. And of course, there are further directions about how to generalize and how to apply this randomized batch size methodology in different examples. And here, first of all, I will tell about possible generalization, which are related to the dependence on the mixing time, because all this theoretical optimality requires that we know mixing time in advance, which is of course a problem. And in the decentralized setting, for example, it's quite hard to estimate heating time, which corresponds to the, for example, communication metrics of a graph. And at the same time, it will be nice to consider applications of this randomized technique, which is shown to be theoretically optimal, to the federated RL setting. We are working on this with Eric. First of all, starting from the policy evaluation problem. Especially for the case where we have a couple of agents who are trying to evaluate a single policy. And probably these agents could act with the additional environmental heterogeneity assumption. So perhaps they could receive different rewards from the environment. So basically, this paper is accepted to NeurIPS, so it's available in the archive. So if you have any questions, please.
Yeah, nice talk. Thanks. One question, I saw the algorithm quite, I'm not sure whether you know that the literature, that paper, I think Li Hua and Mike, I think a few years ago, they have this controlled like variance reduction SCSG algorithm. I think from the algorithm side, it looks pretty similar. Would you like to comment on like the connections or like the improvements over that particular algorithm?
Yes, it's a good question. So first of all, here this randomized batch size, it first of all allows you to reduce the bias which comes in the which is the inherent problem in the Markovian setting. But yeah, for the control of variance, somehow it is hidden beyond this two-level structure that comes from the subtracting like the slower size estimate. Yeah. So yeah. Somehow there are some connections, so you can think about this subtraction as a kind of very specific control variant.
Thank you for the talk. I have a technical question about the assumption of this almost sure bound on the stochastic gradients.
Yeah, so I think I can guess what is the question. Yeah,
yeah.
Of course, it can be strong, but it comes from the fact that we use total variation. We use Markov kernels, which are geometrically ergodic in the sense of total variation, first of all, due to technical reasons. If you want to consider unbounded setting, you need to go beyond the total variation mixing, and you need to consider, for example, weighted Wasserstein metric or something like this. It is possible. So there are results which allows, for example, to do even the p-moment analysis for this setting. But it becomes much more involved technically.
Is it sufficient to assume the same, for example, but with some probability, with high probability that will depend on the batch size, like if you estimate gradient?
It's a good question. I think that potentially yes, but then yeah, you need to be I think careful when you will do kind of union-bound argument in this case. Yeah, but I think that it is probably doable, but maybe more probabilistic viewpoint, more probabilistic solution would be just to consider another types of mixing, which are, for example, which will allow you to control, for example, the functions which are Lipschitz and not only bounded and something like this.
Oh, okay, thank you. And maybe a comment on dependence on delta squared. You say that it's unclear, is it tight or not?
It is clear that it should be present, but it is unclear if it is tight or not in our current bound. Yeah.
I think since it's related and covers zero-order methods, which is delta squared in that case will be proportional to dimension, and this should appear in the upper bound, like it should be proportional to dimension due to Nemirovsky and Yudin lower bounds. So it's, I think, this argument should hold. So you can just, as a special case, because it's very general noise setup, you don't need, I think, to, you can just reduce this to known setup. So, I mean, to the special case. Yeah.
Okay, thank you.
Thanks, Sergey. So we next have Stefanos. Stefanos is a machine learning researcher at Brave in London and was a visiting researcher in the University of Cambridge. His research interest revolves around the areas of distributed computing, machine learning, and mobile and embedded systems. Lately, he's also tapping into the areas of NLP and large language models.
Can you hear me? Yes. Thanks, Pranith, for the introduction and for the invitation. Right, so I'm going to talk about how we can uncover low-rank structures via trainable decompositions. A bit of an introduction, quick one. Researcher at Brave Software. I'm also visiting researcher in the University of Cambridge. Before that, I was at Samsung AI in Cambridge, so very focused on Cambridge, you can see. I did my postgrad there, and I also was an engineer at CERN in Switzerland. My research interests revolve around the areas of distributed ML, mobile systems, efficient deep learning, as well as federated learning, as expected. Right, a few things about Brave, because I talked to a few of you and you didn't know. This is not an advert. Don't use it, I don't mind. Right, so Brave offers an alternative to big tech in terms of the web components. So we have the main product is a browser. And we also have an independent search engine, so it has an independent index. The only alternative is Google and Bing, effectively, to that. And there are a bunch of other products. Right, Brave browser is pushing for privacy by design. So we have integrated ad blocker, and we block third-party tracking and fingerprinting by design. It's Chromium-based, it's open source, and it's available across different platforms. So this privacy sensitivity is creating certain challenges for us. So individual users cannot be addressed. Whatever ML we're doing, it needs to be privacy preserving, and it needs to happen mostly on the foreground. It cannot interfere with the quality of experience to the users. FL participation, since we are anonymized, we don't have a persistent channel to different clients, so it needs to be client-initiated effectively. And certain users cannot leave the device at all. So FL is the only way to move forward with differential privacy or other privacy guarantees. Right. So I'm going to first refer to a bit of a background and motivation about our work. Then I'm going to introduce Maestro, which is uncovering the low-rank trainable manner. And then I'm going to talk about certain challenges and future direction of this work. Right. So everybody knows that neural networks have been getting more and more heavyweight as they become ever more accurate. We're entering the era of hyperscale models, and this takes its toll on the computational side of things. So we have new use cases being put forward, such as self-driving by Tesla, or image in-out painting, such as the Adobe Firefly, web page interaction with various LLMs, such as Brave Leo, or even the voice assistant being put forward by Google on the latest Pixel. So deployment trends include different architectures than in the past. So we have LLMs and transformers, which is apparently all we need. Stable diffusion models, or even neural radiance fields. So at the same time, we have devices that do not have a single model deployed, but multiple models cohabitate the device at the same time, either in the same app or across different applications, and they run at the same time. Indicatively, you can find, like nowadays on devices in your pockets, more than 50 models being resident. And also the privacy has become very important in the agenda of companies and regulators. So we move to techniques that relate to local private inference or even on-device training and personalization. So there are certain bottlenecks when you're running workloads on device. These bottlenecks can vary from energy boundedness, so you can have workloads that cannot really run for a long time in the background. An example here is Android Doze, which is the mechanism that Android uses for putting applications to sleep. So you need to opportunistically train as you have devices, as you have applications in the foreground. You have memory boundedness. So for example, if you want to run an LLM device, you can see that it is largely memory bound. So the accelerator is waiting for the memory, for the weights to be brought from memory to on-chip memory. And also there is the compute boundedness. So when you're fully utilizing the compute throughput of your device, then you're effectively bounded by the theoretical throughput of your device. Right. When we're going distributed, the story is slightly different. So on the distributed training, for example, of hyperscale models, we have the bottleneck being the accelerator interconnection inside the data center. And outside of the data center, you have the wireless link being usually the bottleneck, and specifically the upstream communication. So all these trends, as well as the model size being scaling faster than the hardware advancements, pose for a requirement for algorithmic and infrastructural contributions to sustain these workloads. These include algorithmic contributions in the area of stochastic execution of graphs, such as mixture of experts or early exit networks, bringing down the traffic either in network or like from main memory to on-chip memory. And you can see quantization and low-rank approximations being towards that front. Then more specific solutions to LLMs, such as speculative decoding or token skipping, as well as workload offloading, where you can use, you can leverage external resources that are faster in order to run your workload. Right. Some prior work. We had NeurIPSET 2021 Fjord, which is a resource-aware federated learning training scheme for tackling system heterogeneity through order dropout. I'm going to talk about order dropout, but effectively it's a method for controlling the model footprint in comparison with the resources that you have on device. And then we generalize these into Fedoras, which stands for Federated NAS. It's similar to what Alexei presented before, but it also accounts for the training variation and the capability of devices. So NAS allows for more degrees of freedom in the architecture. And going back to Fjord and order dropout, a brief introduction. It's a mechanism for order or importance-based pruning based on sample nested training. It enables the extraction of submulti training without the need to retrain. And it's parameterized mainly by the p-value, where it ranges from 0 to 1. So at each batch that passes from your network, you take the first p by KL, KL being the width of the model, and the rest is being dropped. So you train that with or without knowledge distillation. Right, so the question is, what if we leverage decomposed representation in a trainable manner in order to target model efficiency? And this is where Maestro comes in. This is fancy icon, comes from OpenAI's DALL-E. So instead of operating on the width of the model, now we're going into the low-rank decomposition of the model. So we first run a decomposition, an SVD decomposition on the layer of the model, and then we're using order dropout effectively on the low-rank representation in order to be able to select to sample the ranks that are being trained, and then progressively pick the more important ranks and remove the redundant ones. Compared to Fjord, we're operating on the decomposed weights, and we're doing independent sampling per layer. So you don't have a uniform p-value anymore, but you're sampling independently per layer. So the training process looks somewhat like this. You start with the SVD decomposition I said before. It applies to different types of networks, linear layers, convolutional, or even transformer layers. You have BI being I and B, sorry. I is the layer. You go for each layer of the network, and B is the rank that you're selecting. And you're computing the loss based on two components. The first one being the learning objective, of course, on the sampled on the sampled ranks, and then we have a hierarchical group lasso loss, which eliminates progressively the unimportant ranks. That means that the unimportant ranks are pushed towards 0. And then we're progressively shrinking, based on these assumptions, the network by pruning away the unimportant ranks based on the epsilon hyperparameter, which is thresholding effectively what your effective 0 is. So this method has some nice theoretical guarantees that for uniform data and linear case, Maestro recovers SVD. And for the linearly transformed data set, Maestro recovers the PCA of the identity mapping. In terms of empirical results, we ran our algorithm on several datasets and models, including vision and text. The training behavior you can see on the left side of the slide. You can see how the total ranks, so the importance across all layers, evolves over training. And you can see that it stabilizes, and also how the ranks per layer are evolving across the network. You can also see for different lambda values. Lambda is the hyperparameter between the group lasso loss and the actual loss, the objective loss. And last, you can see the convergence behavior of Resident 18 on CFAR10, which is quite smooth. We compared with various baselines, including baselines from the low-rank decomposition, from unstructured pruning using lottery ticket hypothesis, being imp and rare gems, binary quantization with XORNet, and you can see that we have competitive accuracy for the same amount of flops or even less. And you can also see how we compare with such methods in the case of transformer architectures. And last, we did sensitivity on the impact of the specific selection of the lambda hyperparameter, so the balance between the two objectives. And you can see how we can trade off accuracy with the number of parameters, because it pushes less of the unimportant ranks or more. And then the ablation study of how the group lasso and the progressive shrinking affects our method. Of course, one can actually deploy either the model that is the result of the progressive shrinking, or even go beyond that, so shrink the model even more by sacrificing some of the accuracy. The way that we do that is that we rank across all layers the importance of the method, and then we start shrinking by the least important ranks. And you can trade off this way accuracy with latency. So you can see for two different models and datasets how this behaves. The SVD model here represents a model that is just factorized through SVD, and we're selecting the ranks that were the output of our method. So it's a post-mortem, let's say, application. And you can see that it is significantly worse. So some challenges of future directions. On the sustainability side of things, we have not really evaluated the energy impact, but we're using model size as a proxy. However, when we're talking about deployments, especially federated learning deployments, where you're training at the edge energy sources are not as green as the most efficient data centers in the world coming from Google or from Meta, for example. So we need to be careful and not use that as an excuse, for example, to become less green. On the guarantees, there is no inherent guarantee about the footprint of the model that we end up with. And the greedy search that I described before for the accuracy latency trade-off is just a starting point that works sufficiently well in our use case. Of course, after pruning, fine-tuning may get some of this lost accuracy back if you have still access to the training data or some training data. And on the scalability side, well, we have hyperscale models and LLMs making their way into production, so they can have a significantly larger search space. So going layer by layer and sampling in that manner might take its toll on the algorithm. So the non-uniform sampling, a non-uniform sampling technique in combination with the use case that you're deploying for may increase the utility and accelerate the training overall. So a shout out to my wonderful collaborators, Samuel, Shoshank, and Honki. And thank you. I hope I'm in time. Jay, thanks.
Do we have any questions? Then maybe I can ask Eric to set up. Thanks again.
Thank you.
Eric Shing is the founding president of MBZUAI. I just found this out by looking at Eric's page. He has 2 PhDs. I didn't know this. He has a PhD from UC Berkeley in computer science, and he also has a PhD in molecular biology, if I read it correctly. He's an assistant. He was a professor at CMU, where he was the founding director of the Center of Machine Learning and Health. And his research interests are the development of machine learning and statistical methodology and large-scale computational systems and architectures for solving hard problems like automated learning and reasoning, decision-making, multimodal and dynamic worlds. We're really lucky to have Eric's support in hosting the workshop, and also really grateful to have him with us today. Thanks, Eric.
All right. No, you don't have to touch it. Yeah. Good morning, everyone. I want to thank you again for coming back, for those of you who were here last year, and also welcome the first-time comers to come to Abu Dhabi and MBZUAI, for this wonderful workshop. And I also appreciate Mike Bernice, to put together such a great program. It's really our honor to host, such a distinguished collection of researchers, to discuss research in a hopefully comfortable and intimate context. I was asked to give a talk. Until this morning, I wasn't sure what I'm going to talk about. Well, I do have a paper at NeurIPS, on federated optimization, but I feel maybe, you guys won't want to see one more such a small technical talk on a particular algorithm. So I dare myself to do something totally different. I want to entertain you, to prepare your appetite for the lunch with something that is kind of crazy and not what you often see, in this context. I'm going to present a rather high-level, broad-stroke, a project, a description of the project that I've been very excited about, without diving into the details. And as also Mike mentioned yesterday, with enough young experts and scientists here talking about all sorts of details. And here I'm going to kind of point my focus on the problems, the bigger problems that we might find new opportunities, or maybe to find that it's total crap and we should move away from that. So don't be afraid of just totally trashing what I talk about. So the title is kind of big, and it reflects my background as a computational scientist, but also a biologist. I want to reflect kind of the path from X-ray crystallography, which was a fundamental, a cornerstone innovation, in biology, all the way to what we saw a few years ago, AlphaFold, and then now the topic of generative biology. And I put a big title there, Renaissance of Empiricism and Connectionism in Biological Science. The title because I used to give this talk once only before in the Royal Society to kind of, again, maybe stimulate, some interesting debates. So, right, so big data-enabled foundation model, it's booming. We saw all these curves. In fact, I think we need to add a few more points now with the publication of the Gemini and a few other latest new models. The important thing to remember is that just in a matter of a few years, 2 or 3 years, we are seeing orders of magnitude increase in the size of the model. And it is defined against all the mathematically inspired laws that we used to describe, sample complexity, overfitting, and all that. Basically, the model keep growing. And also, it appear to be, delivering newer, utilities and functions, right? One thing, of course, is generating everything. It is really generating text, image, plans, a lot of other things. And when you prompt it properly, okay, when you kind of put a text there, maybe you put an image there. And naturally, if I put myself as a very, very ignorant and naive user, I would ask the following. What if I put all this biological stuff that we have been working on for so many years also into, say, a foundation model? If you don't like the word foundation model, you can use pre-trained large models. Fine. Basically, it's a big model that is trained on the big data, which now is biology, or maybe a personalized health record data. And can we also get something, as interesting as, say, a personalized medicine, or maybe even just a daily, healthcare management, right? That's basically what we're kind of getting now from the large language model. You prompt, and then it comes back to you with something quite interesting, at least to a outsider standpoint. This is very different from the now practice of drug design and drug discovery. What we are doing now, still now for the past half a decade or maybe longer, is that you started from a astronomical number of possibilities, compounds, and ingredients. And then you go through multiple stages of literally sifting. Okay, the sifting is by design the experiments without actually knowing the mechanism of how they work. You literally just sift, right? And we have names for all these trials and phase 1, phase 2, and regulatory approval and so forth. At the end of the day, if you are lucky, you'll get one thing out of it. That process usually takes like a decade. And also it takes literally, billions of dollars, right? And that's not, the way we design, our other things like a chip, write a program or, build a building. It is not based, in many cases, at least the full picture of biology. It may be based on a little bit about biological knowledges, but it's not, in fact, we don't even know what is biology, okay, for a cell. As a biologist, I can tell you we don't know too much, even though we feel like we know. We invent words like a network, regulatory, circuitry, and all that kind of thing. I tell you, these things doesn't exist physically in the cell, okay? It's just our way of describing what's happening, okay? It appears to be a first principle, but it's actually not quite there yet. Okay, you cannot, for example, put up an equation and do some calculation and start to compute the outcome, of a cell response for anything, right? So that's not based on first principle. And so can we replace this whole thing, with, for example, a foundation model? That's kind of the question I've been asking, right? What prevents that from happening in the past? Well, primarily because biological systems, as we all know, it's very complex. It's probably more complex than our language, okay, on which we are, training, for large language models. Look at the number of, total number of atoms, molecules, in their interactions at all different levels, and then perturbation interventions, and then, of course, space and time, all that. It's this myriad of biological ingredients and the components are really extremely complicated. And in the past, the way we studied actually is a very empirical approach. Okay, we started collecting data of all kinds. Okay, modern day biology started exactly from a new way of collecting data, which is in here. Okay, in 1950, that era, you use an X-ray to shine, a crystallized piece of molecule. You get their shadow, and then you compute through the Planck equation and the reverse kind of a guess or compute the structure. It is not through first principle. Okay, and then we continue to gather more data. In fact, the whole history of modern biology is about new technologies, of getting data, and maybe some ways of disturbing and interfering or changing the system. We measure gene expression. That was the time when I was a graduate student. It's a big deal, measuring a few thousand genes and put them onto a matrix and do something. One of my first papers with Mike was to do feature selection, in these 20,000 genes and get the informative ones out of it. And then there are all these evolution of new techniques, and now we can actually measure the gene, or maybe we call mRNA, which is a precursor of the protein, in terms of their intensity and the volume in a single cell, okay, space and time specific. But on the other hand, this is very different from we set up a camera and looking a one cell continuously growing across time and space. Okay, once you measure, the cell is gone. You have to do another thing. Therefore, there is a lot of amount of statistics, mathematics involved to even make sense of the data that you collect from actually different systems, and then put them together, and then tell a story. Right? And the volume of data right now is actually quite big already. People don't realize that, but we actually have the same type of avalanche of data as we see in the internet about the web, in the text and the image. For example, there are tens of hundreds of millions of sequences, of individuals and species. There are hundreds of millions of single-cell experiments, being documented and reported. And across the spectrum, we are talking literally at the order of hundreds of millions, if not bigger. And this number is growing very fast. And again, there are techniques, many of them well statistically and mathematically motivated to analyze all these. So here are just examples of that. And that basically is how biology is done now. Okay, it's very much like in our linguistic world, we put a particular dialect, maybe in a special topic, let's say, classical literature, and then hand it to a lab, and they basically study, everything there. And then another language, another topic, and it's very siloed, okay? And for a good reason, because the classical approach, like this one, we use to study biology, were kind of based on an implicit assumption of small data, okay? Sorry, I think I'm pointing to the wrong direction, yeah. And therefore, we actually, in fact, our very educational system, in the university was established to honor such a siloedness. For example, we established a department of cell biology. We also have departments of molecular biology. We have the department of microbiology. And then all the way up, you have plant science, animal science. Then in the hospital, every organ of your cell becomes a division. You have a division of a liver, a division of a brain, and so on and so forth. It's all kind of cut apart. And imagine that when a patient goes to a hospital and he is sick, all over, you can imagine what happens. The doctors from different divisions were called together. Even to sit in the same room and speak the same language is already a big deal. But at the end of the day, it's actually important to realize that we actually are looking probably at one organism, one instance of an organism, which is a human being or a cell. And the DNA, the protein, the cell, the tissue, everything actually is just a different granularity of the same thing. Okay, that's actually very important. It's the same thing, but it's actually coming from different granularity, right? And now they are studied in a completely or very much siloed way, okay, in a non-community. So, the natural question, and I think the reason is because of resource limitation and capacity limitation, because we don't have the right tool, for example, to put them together. But now we are in a new era of these large pre-trained models. Like it or not, they show us already a few instances about when you put everything together before you even know everything. Okay, you just put all the languages, all the text instances, everything together. Before you even read it, something interesting happened. Okay, also before we even know why, but it happened, right? So that actually challenged us the question, if there is a way that you at least have the storage of store all data together, and if you have, say, 10,000 GPUs, and if you have that amount of infrastructure and people, are you still going to create 100 departments and divide your machines and data to all of them, or you want to group them together and do it slightly different way, right? So that's actually what also MBZUAI is about. The reason I came here and built this school is exactly to see the alternative, which is something not done in established schools and companies, that when you have such a big resource, or maybe a big question, and also when data become abundant, maybe you want to do something differently, right? So that's kind of the gist of this talk, which is again very high level. We want to see a way to move away from all this classical, approach, which are largely, analytical and, reductionist. That's actually where we were trained and we are very good at, into something that is a little bit crazy, okay, and less elegant. The LSMs, the transformers, the bigger models, yeah, they are very dirty and ad hoc, but just like the first microscope was invented, it was, actually really causing people to rethink how they do biology, right? So that's basically, what I want to, maybe speak a few more words. There are two paths in the past, in biological research. It's always been the case. There are people who, come from this highly, rigorous, technical background, championing rationalism and reductionism, and the word there is, let's look at causality, let's extract first principle, let's use the law of physics and mathematics, to really do things extremely elegantly, predictively, and provably, right? And that's actually how we, for example, compute the ellipse. You can actually compute the timing of the ellipse, based on some very simple laws nowadays, and to a great deal of satisfaction. It becomes even a fun thing that on CNN and Fox, you will announce, hey, at a particular moment in the United States, you should show up. If you're good weather, you will see something magical, right? That's a very, very beautiful accomplishment of first principle and the reductionism approach to science. And it really, really, gets you the satisfaction and also the confidence. But unfortunately, symbolism and the computationalism scale very poorly, especially in the problem of big complexity, such as in biology. In fact, we all know that as a physicist, you cannot even use first principle to compute the very interaction of maybe 3 bodies or 4 bodies, right? And any biological molecule has millions of atoms already. So that path actually isn't getting us to what we want. Then comes the empiricism and the connectionism, which is based on trial and error, data-driven, and sometimes it's a black box. Okay. In fact, the biologists who use electron microscope, or fancy atomic force, they don't know a thing about how it worked. They use it anyway. To them, it is a black box. To the physicists, it's not, but to them, it is. But it doesn't prevent them from using it. And also, it generates some kind of understanding, again, very different from there. Okay, the understanding is not about the orbits, of the whole thing, and also, the law in the form of a few equations. It's really in the form of a empirical understanding that is focusing on actionability. You want to do something. So I want to give you the example of how vaccine was discovered. Vaccine was discovered in the day before we know DNA, before we know protein, before we actually know the modern picture of biology and the cell, right? And Pasteur basically did a bunch of experiments. And he found that, when some animals, were intentionally, contaminated or infected with a dead form or a very weak form of the disease or the virus, they actually become immune to the real form, of the disease. I have to take some more time, sorry, for that, right? And the result was repeatable, okay? And also, it became highly actionable. Okay, before you know any Y, any genetics, any genes, you just immune or inoculate that guy with a weak form of the vaccine of the antigen, and you're done. And how to treat that antigen is also very well documented. So I call them actionable empirical understanding. You focus on the utility of that. Right, so I guess, I want to pass this page. There's a whole kind of history of the success of empiricism, especially in biology, because maybe biology is so complicated. People just, have to make some progress before you know everything. For example, our very knowledge about the embryogenesis, okay? We have a full picture of embryogenesis right now of human and of this little animal called Drosophila. This looks like a movie, right? It's actually not a movie. It's not that you have a little, video recorder looking at the thing being dividing. It's actually stitched together from tens of thousands of pictures taking on different embryos at different stages and so forth, but then they put together. So this is not a causal inference, not a real-time recording. It's literally a reconstruction of the process based on a very strange sampling process. And then, of course, X-ray crystallography, right? What happens is that you basically make a crystal out of the protein, which is already not a native form of the protein because they're crystallized. Then you shine the X-ray, you create all this very complicated form of the shadows. And then you run some programs, which is a complex form of linear or nonlinear kind of deconvolution, of the information, and then you kind of figure out the protein. In a sense, what we see as a protein structure here is not in a rigorous form what we see. We didn't see anything, okay? It is an output of a computation, okay? And also an output of the way you prepare the form, the samples. Right. And now what's happening with AlphaFold is just this part is replaced by a program. Okay. Not that basically disturbing if you actually know how the original experiment was done. Yeah, so this is basically what's used nowadays in many of the largest models. Layers of tensor operators, right? Starting from some attention based on linear operation over the inputs and some transformed form of the inputs. And then you have an array of those attention heads. Then you have a stack of these arrays of attentions, and you call them an encoder. And then you have multiple encoders arranged in a certain way. You have a transformer, right? And you can also reverse that. If you look at this, I actually, when I try to explain this to, say, a non-scientist, I actually all of a sudden came to the realization that this is no different from the optical or electrical microscope that we use in biology. What is a microscope? Okay, you put optical lens in here. Okay, you maybe put also electrical fields there to replace the optical lens, and you manipulate the beams of lights or the beams of particles and so forth. And this is actually, like what transformer is doing you, or what the attention and the tensor operator doing you, to kind of linearly twist, fold, and merge, and multiply, the information. So it's a way of processing information. Microscope is actually maybe the earliest kind of fancy way of processing information, visual information, through many steps of operations, right? And what the biologists saw, in the final step, it's not verified, by the way. We didn't see the real thing, okay? It's based on some kind of, experimentation and some part of theory. The theory is not about the physics of the biology. It's a theory about how these informations are processed. And then you build a confidence that, hey, I should trust that. Well, in a sense, what Transformer does is exactly that. They are basically doing some manipulation of your textual kind of tokens, or maybe imagery tokens, and then you put there something. If you believe that makes sense, and if you believe that it's repeatable, and if you believe that it is satisfying certain statistical behavior like stabilities and robustness and so forth, you choose to believe it. And then this becomes your microscope. That's the way I see it, right? And therefore, when I put the biological data in there, I do hope that over there, when it is being synthesized and generated in the decoder, maybe we could see biology itself, just like what we see visually from a microscope. Right? So that's the kind of the rationale behind this whole idea about redoing biology using the large pre-trained model. Again, there's a whole zoo of pre-trained models in the space already in text, image, audio, video, and so on. Not yet too many in biology, but they start to appear. For example, AlphaFold is actually a very, very matriculate engineering feast, right? So it basically has some ideas that is unique to biology. For example, in here, there is an input representing the structure. How you use the structure? You use the structure to create now the pairwise distances between all the atoms in your sequence. That gives you a two-dimensional display of the information. It's kind of a way of imaging the protein as a training information. And then the sequence, if you just put it by itself, maybe already informative, but not quite. They put together multiple sequence alignments so that you see, across a species, which part of the sequence is more conserved than others, and that gives you the way to pivot into this matrix to actually weight them differently, right? And then through some kind of, multiple folds of attention integration and layer transformation, you basically are doing the same thing as you do with language using the large language model. And then you can actually make some more empirical steps to recycle the output in here and refine the weights. I think this is just when you train the RBMs or something, you actually have a way to unfold a two-layer RBM into multiple layers of fixed weight kind of propagational procedure. I think this is something similar to that in terms of the high spirit, right? But at the end of the day, you were able to predict based only on the sequence about the structure, which is in a sense to me a digital microscope should do, right? And in fact, this is a model built by my colleague Le Song, which is fancier. You replace multiple sequence alignment now with a language model, with a protein language model. Basically, you pre-train that multiple sequences only based on certain ways of tokenization, certain ways of attention mechanism. And then that actually becomes more efficient because multiple sequence alignment is very, very expensive to form during inference. And also, you can only build on a few sequences in alignment, maybe tens or hundreds. But in here, you can train that protein language model with all the sequences you ever have in your database, which is very rich. And they actually gives you functions, like predicting fine structures, predicting interacting structures, and so forth, right? So that's kind of a roadmap that my team is trying to now push forward. That you can start using this type of technique, first of all, to process a large amount of data, because by definition, these are heavily parameterized models, which needs a large amount of data to be trained. And then also, they are intrinsically able to combine multimodal information. We already see AlphaFold as a combination of a sequence and structures, right? And nowadays, people are working on single-cell models as well, where the gene expression counts over all single cells, but also the gene ontologies, the networks of dependencies of genes or proteins can also be encoded to, it's almost like the equivalent of positional encoding in the words. Here, the genes are not positionally encoded per se because they don't have a position. But they have their functional kind of a position inside a network or inside an ontology. You can kind of blend that in. So these models are allowing large biological data and also cross-modal biological data to be naturally integrated. And we ask, what if we just build a bigger enough model that integrates all of that? Wouldn't that be equivalent of modern-day large language model biology? We don't know, okay? But it's actually at least something intriguing to try if you have the resource. Right? So that's kind of the rationale behind our project. It's not totally crazy, but it's a little bit crazy because we don't actually know what to come out of it. Okay. And well, just to give some confidence of ourselves and maybe to you guys, when we do less ambitious, only single model, foundation model training, we found that whenever we're able to successfully produce it, here are examples of the model we already produced. Some are very big already, a 100 billion protein language model. Some are small, like 100 million single cell model and so forth. For each of these models, we were able to establish the SOTA results of all the downstream tasks people originally collected sample for. Okay, for example, in biology or in protein, you want to do more than structure prediction, right? You want to probably do the docking prediction, whether two proteins stick together, maybe the affinity prediction, how strong they stick together, right? And also mutation fitness. If you mutate something, do you still see the right structure or not? So that's a typical downstream task of protein, and there could be a dozen of that. And in single cell, of course, the trivial thing will be predicting cell types and morphology, but you can actually also try drug response. You perturb the cell by applying a chemical compound or drug. And in the drug industry, this is a big deal. You have to do a lot of wet lab experiment or controlled experiment. But in here, you can also use a model to predict. And the CRISPR perturbation is another thing. You just edit the gene a little bit and see what will come out of it. So what I meant to say that across the 7 models that we trained and across all the tasks that we gathered from the literature to make the performance, we were able to substantially overperform the state of the art, or at least tie with that. And the other performers who are good are also foundation model trained elsewhere. So that kind of suggests that this particular approach at least is showing a good sign of dominating over the traditional approaches, which are based on very task-specific. For example, you train a model to predict the response of gene perturbation. You train another model to do other things. In here, the approach is, by definition, multitask and transferable. And also, of course, once the model is given and pre-trained, hopefully, just like what we do with large language model, your customization, your specific alignments of human taste and needs and the safety and so forth becomes a fine-tuning and the prompting. Again, the math is not clear, but it is being practiced with good empirical outcome. In biology, imagine that you could translate that language of tuning and prompting into our personalization of health conditions and drugs and so forth. So in a sense, there is a way to close the loop using, say, a reinforcement learning to do it iteratively and to address many interesting biological problems. So here are just some example of using the model we trained to do structured design. You want a particular antibody to demonstrate a specific structure that can grab the antigen more efficiently. You should probably be able to do that with a totally in silico experiment based on the model. You can also try to model 2 proteins together to see their interaction and so forth. Right. So just to back to the closing finishing line. So what I just talked about is something different from what many of us, including myself, practiced in the past in machine learning. Here, it is really, from the sequence structure is not using this approach where we have a good equation that allows us to compute everything predictively and confidently or we have a periodic table that when we mix two compounds, we know actually exactly the chemical behavior of something next downstream. We don't have the luxury. And we can say that, okay, let's focus on a mass and wait for another years before that happens. Well, I don't believe in 100 years we can use mass to compute a structure. Honestly, it's just too complex. But in here, the approach is a completely paradigm shift. You train those slightly more mysterious large pre-trained models, and then you fine-tune and utilize it. And along the way, you perfect it. This is actually how, at least in my opinion, microscope, again, back to that story, was actually practiced. Originally, they were just two pieces of glasses stuck together and see something fancy, and then gets fine-tuned, refined by Carl Zeiss and some other physicists, in fact, who studied optics. And then by the atomic scientists to start change the beam from optical lights to electrons and to other kind of atomic beams. And you actually get more and more magnification power with a lot of good science in that. But the science is not about the subjects. The science is about the vehicle that you get there, right? And those inventions actually had very little to do with biology itself, but biology become the best benefiter of those inventions. And here, we want to see whether with the digital age, with the new foundation models and the deep learning and all that, can biology once again have a paradigm shift away from those old. Okay, these are some graphs we all know. Scaling laws, you can actually even either empirically or maybe theoretically study the complexity of a sample, or maybe providing guideline about how much data and how big a model you need before you kind of reach to the limit. And this emergent property, some of you have heard about, is a kind of still mysterious. We don't actually know what's going on, but we saw those curves already up to a certain size. And given certain data, you see a sudden jump, of some, interesting behaviors and capabilities. Maybe due to the inner connection inside the data that we don't know, but picked up by the machines. Right. In our recent production of the JACE model, for example, you probably heard it's Arabic, large language model we trained here. It was funny that when the Malaysian president or prime minister came here, and when our team was trying to make a little prep, they found that the language model actually could understand a fair amount of Malay language, even though it's never trained in our model. Right. So that's the kind of emergent property, at least I would be curious to see, when we have the biological models, being, trained in that fashion. Okay, just to wrap up, I think we have the opportunity to welcome a new platform or paradigm for the holistic life science in a way different from others, from before, where all this data gets, gathered and integrated, and then hopefully solve not just one task, but a whole spectrum of tasks against a single same object, but at different level of granularity. Okay, using a holistic model. Again, of course, I don't know how long it will take to get there, but it might be an interesting kind of North Star, to look at it. So to sum up, there's a contrast between LM and what I call the LBM. They have some great deal of a similarity, at least spiritually, and in principle, of course, the actual nuance will be very different. In here, I think the effort that we face is the tedious ones. How to design, for example, the right tokenization of the data, right? How to design the right internal representations, of those latent features, and how to come up with the right architecture to allow information to flow the way we want it. So these are, in some sense, very engineering, exactly like how people design the good old day microscope. But I think this is still, a useful direction, at least for computer scientists. That's basically what computer scientists were trained for. They need to basically make tools, right? So that's where I want to end the talk. But ideally, going back to where I personally came from and the like, I do not see, the rationalism and reductionism, that we practice versus the empiricism and the connectionism that are currently becoming hot. I don't think they are really two parallel paths never meet, right? I think they can cross-inspire each other and provide problems. For example, the model itself could be explained, at least in parts, if we have the right kind of way to look into it. And I don't think also, the models we see now are really calling for bypass first principles, right? You actually could, maybe design the right experiment to recover the natural laws, based on new findings. So the hope is that these two trends or two schools, can evolve, hands in hand to really meet in midway. That way, in the future, enjoy a new, technical paradigm, for biological science that is both, rigorous and, technically, mathematically explainable and provable, but on the other hand, really, hopefully not requiring us to take heavy assumptions and walk away from real life dirty and big data. So with that, I'm done.
Questions for Eric? Yes.
So I'm curious, why did you not keep going in terms of, why did you only take biological data, not language data as well, and form one gigantic model that has everything? And where do we draw the line? Because your theory is we need to have these foundation models that understand across all these different domains and holistically. So why not keep going?
Very good question. And I have a very kind of, how should I say, unfriendly, hostile answer, to people on either side. We are talking about, when I talk about biology, or when biologists are talking biology, it's the language of the God. It is basically how DNA, protein, and other things function inside a living organism. The natural language is for human being to consume, to understand, to entertain, to understand that part, right? If your goal is to understand that and also articulate and communicate, you may need human language. But if your goal is to really uncover the truth, just like many of you like to write the equations without bothering giving any explanations, right? So that to itself is enough. In a sense, the language, the human language, the NLP, to me is a contamination to that information because there are a lot of inaccuracy there as well as information. For the information that is already there, they should already also in the biological data. You can rediscover it. So there is no need to get the human part of that. But for the information that is incorrect, they become noise. So if you truly trust there is a need for paradigm shift, say using this foundation model and so forth, why not begin with the clean intrinsic data and leave this extrinsic one outside? And then what you can reconcile later if you want to tell a story out of it. You want to create an interface for an individual to manipulate, to produce outcomes by typing human language. Well, that's a utility goal, not the original goal of the model.
I mean, so if I were to push back, I would say that for LLMs, they train them on coding, math, and sciences, and maybe there's a lot of interesting things that could help us resolve some of the questions, right? Yeah. There's logic, and there's structure, and there's mathematics and whatnot. So I don't know. I mean, I agree with what you're saying.
Yeah, this is a philosophical thing. Yeah, you are human-centric. I'm Mother Nature-centric in this particular case.
Maybe I have a question.
Yeah.
So for these, there's a reason, it's easier to believe that having a language model is possible, like understanding language is possible because we as humans do. So there's already like a proof of concept of like a system which can process, create, and understand language, whereas for biology, no one understands it. So it's not even clear if this goal is even possible.
Mm-hmm. Yeah, that's why I kind of coined the word, the actionable empirical understanding. In a sense, we should humble a little bit, not to say that, hey, only if I understand it, it becomes a truth. right? If it produces something that is repeatable and actionable and creates the results you want, maybe that's okay to begin with. So that's kind of how I take on this approach. Say this AlphaFold thing. I think it's an overwhelming success by all measure, even though people argue against it for certain little tiny accuracy. But it does produce you the structure you want. What else, right? So I would say, yeah, in biology, many of the goals and also the laws, like for example, this law that I don't like is the so-called gene regulatory network. It is a pure artificial thing invented for our little brain, for our very, very poor brain to understand a very complex phenomenon. Then we invent the word network. It is not producing any output because you cannot simulate this network to generate results. So it's for a conceptual understanding of the relationship. Yeah, if you use that as a bottleneck, you will be stuck in the bottleneck. Right? I've been working on gene network for a decade, and I don't really get out of it, honestly, with anything useful. But if you say, my goal is to predict a cell morphology based on some perturbation, what if I just bypass that network thing, and here I have a black box model, which actually gives you that prediction that you want, repetitively. So in a sense, you are on a different paradigm.
So another question not related to the others. Do you see privacy as being a blocker here for achieving this vision that you're pitching? Because for language models, there's a lot of text on the web, right? And we can just scrape it off and train these very large models with trillions of tokens. But for this to be able to achieve it, we need a ton of data. And I suppose that data is either not accessible, we don't have a massive data set that has patient records. There's a lot of sensitivity and privacy concerns. Should we let go and just go build that vision?
That's another question I often encounter. People already mix up healthcare versus biology. Okay, biology as the basis. You are talking about a novel, or something fancy out of language. I'm talking about the basis of language. On that biological part, there is no such a thing called patient privacy and everything, because it's pure intrinsic information without a human name attached to it. The human name attached to it is meaningless. All you need is number one, number two, telling them they are different. That's it. Right? So for that data, actually, there is, thanks to the very good tradition in biology, every time you publish a Nature and a Science paper, you are obliged to surrender your data to the public. It's been a tradition for 20 years. So many people thought biological data are scarce and not available. That's wrong. Okay, if you look at the PDB database, you look at the GenBank, and there are tons of data out there. It's literally that no one can use it. Okay, the bottleneck is not the data. The bottleneck is that how people can use it right now. There's very few people can use it. Now, clinical data, that's actually exactly the topic in here. When you get a big model, maybe we need to federate it, we need to talk about privacy, and that's the next step. You have a pre-trained thing that is based on public data, and you can fine-tune it. You can specialize it through federation or through privacy-sensitive approach. So these are two different problems. They are not together, right? So we don't need actually patient data, his body temperature and so forth, or his address and the wealth and income to train this model. It has nothing to do with that. Biology doesn't need that. Right? So this is actually very important because somehow this whole space has been so contaminated with human perception that we thought we need this and that. The truth is that you don't need it. Okay, I hope I prepare you well for the appetite because it's kind of a crazy discussion. So thank you very much. Enjoy your lunch.
Thanks, Eric. So for the lunch, I think we're set up in the same place as yesterday. Yeah, and we follow Philip. And the goal is to try come back within an hour so that we can do a poster session and meet the students here. See you again in an hour or so. So just to clarify, right now it's 12:45. Hopefully we'll see everyone back at 1:45.